So a skeleton and muscle model might be another option if you're working in biomechanics or rehabilitation. Depending on what you want to do, you're going to choose a different representation. And the same thing can be said about the way that you model your motion. Right? So on one end of the spectrum, we can have a kinematic model. So kinematic means that we're only worried about how the body is moving. So how are the joints moving in 3D space? Maybe we want to take into consideration some physics constraints. So we want to make sure that the feet are on the ground. There's not some kind of weird foot sliding when we estimate pose. We might take that a step further and go into a physics simulator, something like Mujoko. And in that case, we're going to ensure that there's definitely no foot sliding because the human body pose or that motion model needs to abide by the laws of physics. Okay. And something that's maybe a little bit more popular these days is real world actuation. So can you take your motion model and will it actually work in the real world on a robot? So we have the spectrum. We could have on one end, just really no physics. And then the other end, it's full on real world physics. So what kind of motion model should we use? And the answer to this and the representation question before is it really depends. It depends on what you want to do, right? If you have an end application in mind, or if there's some niche that you want to work on. So what are some examples? So if you're on the spectrum of motion modeling, maybe all you're interested in really is a rough motion estimate of what a person is doing, right? So this is a pretty standard computer vision task. You give me a video, just give me a rough estimate of a person's motion. Maybe all you need is a kinematic model. Maybe you'll introduce some physics constraints. But what if we're now talking about motion generation? So motion generation maybe is going to require some more physics, right? When you generate human motion, you want it to be feet are not sliding, the people are like not walking into objects and things like that. What if you want to estimate motion? Or sorry, if you want to imitate motion. So you want to be able to look at some videos or some examples of people moving and you want to imitate it, but in a simulated world, then maybe you need some kind of physics simulation. And then at the end of the spectrum, if you want to do full physical embodiment, like you want to be able to look at human motion and mimic it with a robot, then you're going to need a real robot. You're going to need a motion model that works with a real robot. Okay. So there's this whole spectrum. Something that our lab has been working on for maybe the last like 6-7 years is this idea of using physics simulation to help with human pose estimation. So it all started really with the problem of egocentric pose estimation. So maybe 15 years ago, I started working in first-person vision. And something really challenging about first-person vision, so when you have a wearable camera and you want to estimate the camera wearer's body, you can't see the body most of the time, right? So it's a really, really under-constrained problem. And the idea that we had was, well, we could use physics. We know that the body is one piece. It needs to abide by the rules of physics. Could we use that as an extra constraint to estimate human pose? And like I mentioned before, the simulated dynamics or using a physics simulator can also be used for robotic imitation. Right, so I'm going to give you a brief overview of some works in this direction. So this is the paper that Zen will be presenting this week at CVPR. It's called Real-Time Simulated Avatar from Head-Mounted Sensors. And the idea is to take a VR headset, and in this case, we see the Quest 2. And the VR headset has several cameras on it. So you see the camera video at the top left. And we're going to use that as input. And what we want to estimate is the pose of the camera wearer, which is in green here. Okay. The bottom right, this is a third-person camera just for reference. So you could see what it looks like. And then the bottom left here is just the mesh rendering. Right, so this is a joint work with Zen, Jinkun, Rawal, Alex, Jing, myself, and Weipeng between CMU and Meta. All right, so let me formally define this machine learning problem that we're trying to solve. We have as input two types of input. One is going to be egocentric video. So this is an example of the Quest 2. The Quest 2 has 4 SLAM cameras. There's 2 looking down, 2 looking outwards. So you see 4 videos there. And then the headset also has a real-time SLAM on it, so we can get the headset trajectory P. So we're going to take these 2 sources of information as input, and we want to learn that function F, which is going to return to us the full body of the camera wear, the full body pose. All right. So we have some problems here, like I mentioned before. Even though we have 4 cameras on the headsets, the body is not always visible. And so this is a very under-constrained problem. So the idea that we have, and which we've used in multiple papers, is to use a physics simulation or the laws of physics as a type of auxiliary signal or additional constraints to solve for 3D body pose. Okay, so the idea of using physics simulation seems kind of cool, all right, but when you want to use physics simulation, what you have to do is you have to be able to estimate body actuation. So what I mean by body actuation is it's not enough to know the joint angle of the person. You have to know how hard how much power they're putting into the joint to move their body. Okay. So the problem gets a little bit harder. All right, so I'm gonna break down the model for you into several parts. The first part we have to do is we have to solve for this policy pi, which takes as input the egocentric video, right? The headset pose. And because we're running this as simulation, we also need to know our estimated current pose of the person. Taking these 3 things as input, we now need to estimate the joint actuation. So for every joint in the body, we need to know how much power is being applied. And that's going to be our first step, right? Once we've estimated how much power is being applied to each of the joints, we're now going to take this actuation and we're going to send this to a physics simulator. So the physics simulator knows the current humanoid pose and how much power is being applied to each joint. And it's going to tell us what the body pose is going to look like in the next time step. So that's how the physics simulator works. When you do that, you'll get a new pose of the person, and then that pose gets fed back again, and we repeat this process. What we see there in the blue box there, that's called a policy or sometimes a controller if you're in optimal control or control theory, right? And that physics simulator in more general is called like the environment or the system or the plant, depending on which area of control you're working in. All right. What happens is this policy and the physics simulator, if you combine them together and you want to kind of look at this as a black box, that whole thing right there is the pose estimator. Right? You're taking the input, it's like figuring out this actuation, puts it through a physics simulator, and it gives you a pose out. So that middle section there is a pose estimator. Now, the tricky thing is, though, in order to learn this physics simulator, we have to figure out what the actuation is. So how do we get the joint torques? So we have a prior paper on this that Zen wrote that allows us to get a supervised signal for this actuation. So this is another paper from ICCB 2023. It's called the Perpetual Humanoid Controller. And what that paper showed was that in physics simulation, if you have some motion pattern, like human motion sequence that you want to match, you can use this PHC policy, and it will compute for you what the actuations are to match that target motion sequence. So that controller pi PHC is very robust, and we showed that it can is it 100% or 90? 100%. Okay, 100% mimic the AMOS dataset, which is a very large motion capture dataset. Okay. All right. So now, in order to learn that pose estimator on the top, we have to figure out what the actuation is at every time step. In order to train that policy pi sim XR, we get a supervisory signal from pi PHC. This is giving us the, you could treat this as the ground truth actuation. And we're going to look at the difference between that actuation, formulate a loss, which is just the difference in actuation, and use that as a supervised signal to train the blue box pi sim XR. Okay, so good. So a lot of the details I have skipped, obviously, they're in the paper, but let's see some of these results. All right. Okay, so prior to the results, we had to make some synthetic data for this paper. It's mostly because it was very expensive to get ground truth 3D body pose with XR headsets. Okay, so this is just giving you an example of some of the simulated data that we use. So we could grab a motion capture sequence from some motion capture data set, and we can synthesize what the body would look like in the 4 cameras. And all that flashing is coming from the fact that we're changing the background at every frame so that our computer vision features are very robust. Okay. All right, so here are some results. So on Quest 2, if you remember, Quest 2 has 4 cameras, has 4 SLAM cameras. We see the 4 cameras up at the top left. The bottom right is a third-person point of view just for reference. This is not input. And then the estimated pose is there in the middle with the green humanoid. Okay, and this is Jinkun showing off his advanced martial arts. Okay. All right, so we did the same thing with the Aria Glass. So Aria Glass, if you know, has 2 cameras or 3 cameras, right, left, and center. Okay, this is showing, I think, results just for the single view. Again, at the top, you see the Aria Glass input. Then you see the estimated pose there in the middle. See, how are you doing on time? I have until, how much? Till 10? Okay. All right. So that paper kind of showed you how it's possible to use physics simulation to estimate 3D human body pose, even when we have kind of this poor sensing where we don't see most of the body. Okay. So kind of showed that that's sufficient for motion imitation. But what about real world actuation? So this is fresh off the press, where we've taken these ideas that Zen has developed for these XR headsets and then applied them to a humanoid robot. Great. So what we've seen there is that because we've developed a motion model that's inherently an optimal controller, I wouldn't say it's easy, but it makes it a lot easier to transfer to real world robotics. All right. So the example up to now, if you'll notice, everybody was like this with open hands. Okay. There's no hand modeling. What about hands? Okay. How should we model hands? Hands are also part of the body. What kind of representations can we use? And what are the different applications that it might enable? All right. So this is another paper that we'll be presenting at CVPR this week. It's called GHOP. This logo should be funny to you if you're in the US. Otherwise, it makes no sense. Okay. GHOP stands for Generative Hand Object Prior for Interaction Reconstruction and Grasp Synthesis. This is work with Judy, Abhinav, myself, and Shubham at CMU. All right. So the problem that we want to address in this paper, as in many other papers, is can we learn the distribution over hands and objects and how they interact? if we abstract this kind of as a formalized machine learning model, as input, what we want is a short text description, like a hand is holding up a cup. We wanted to put it into some function, and we wanted to generate both the object and the hand. In this picture, they're separate, but in contact with each other, right? So what kind of internal representations can we use and should we use, right? So in this paper, we decided to use a mesh model for the object and then key points for the hands. So why mesh model for the object? Objects can take many shapes, many sizes. It's very hard to parameterize an object in terms of key points, right? So we're going to use a mesh. And then for the hands, hands usually have a standard shape. So we could assume that we're going to have consistent key points. All right. So the representation we use is called an interaction grid. It's going to be a representation that concatenates the object information and the hand information. So for the object, we're going to compute a signed distance function, SDF, and then we're going to compress that using encoder decoder. So we have some low dimensional representation of object shape. Okay. For the hand, we're going to use the mono model, but we're going to convert it. We're going to extract all of the key points, and we're going to convert it into a volume of skeletal distance fields. So what is a skeletal distance field? Just says for one key point on your hand, in wherever you are in 3D space, how far away are you from that key point? Right. So if you have 15 key points on the hand, you're going to have 15 volumes. Right. Okay, so these are the two representations for hand and object, and we're going to concatenate them together, which gives us X. Right. So X brings together the object representation and the hand representation, and we call this interaction grid. Okay. So this is our representation. How are we going to learn to generate this interaction between hands and objects? We're going to use a diffusion model. So this is the model I showed earlier. We're going to have a text description coming in, and we want to know how the hand and the object should be interacting. In order to make this a diffusion model, we're also going to add another input, which is some noise. So the noise is going to be a volume. It's supposed to be a noisy representation of this interaction grid. Right? Okay. Okay, so I think many of you are already familiar with the diffusion models. So what this diffusion model is going to do is it's going to take this interaction grid, which is just filled with all noise. It's going to repeatedly call our diffusion function. Right, so it's taking whatever the noise volume is, estimating what the residual is, and then computing kind of a cleaned up version of it after multiple steps. It's going to be conditioned on the text description C, which is hand holding the mug. And then at the very end of our diffusion process, we'll a full and clean interaction grid, which, if you recall, contains the object shape and the hand shape or the hand pose. Okay. In a common reference frame so that they're interacting with each other. Okay. So more of the details, again, are in the paper, but here's some examples of GHOP and what it can generate. So if you give it a sentence that says a hand holding a power drill, it will generate something that looks like a power drill and an appropriate hand grasp that's holding that power drill. And you see a bunch of other examples there as well. All right, so now we have this diffusion-based hand-object interaction generator. What else can you use it for? So in the paper, we're going to show that it could be used for two things. One is interaction reconstruction. So this is where you're actually given a video of a hand interacting with an object, and we're going to use this GHOP model to estimate the 3D pose and shape of the object in the hand. And then the second one is just pose synthesis. We're going to give GHOP a shape, and then we're going to say, how would you grab this shape? And then we'll generate the different ways to grab it. All right, so just showing you some results. You'll see the video on the left, and then you'll see the estimated 3D hand and object meshes there, viewed from two different angles. And then this is the grasp generation. So the input is going to be an object shape, object mesh. And then you'll see 3 different grasps that were generated from, from different angles. Okay, great. So that's the GHOT paper. Again, there'll be more details at the poster session. I believe that it's sufficient for motion estimation. I kind of gave an example of that in the videos. But if you'll notice, the hand is disembodied. So the hand is not connected to anything. We've kind of like normalized the rest of the body away, right? So the model is not sufficient for motion estimation, right? Sorry, motion imitation, at least for like full body motion imitation. So this is another work that we've been working on. This is again from Zan Jinkun, Sami Alex, myself, and Weipeng. And it is called Omnigrasp, grasping diverse objects with simulated humanoids. So now we're bringing the body motion and the hand motion and finger motion and object interaction all into one. Okay. Again, we're taking this physics-based approach. So I kind of explained to you the framework of this earlier. Now it just has a little bit more input types. So what we want to do is we want to learn this policy, pi omnigrasp, which takes a bunch of observations and then gives us the torques or the actions to actuate the full body, including the fingers. Okay. As input, we're going to have the object state. So we're going to assume that we know the 6th degree of freedom, let's see, orientation or the pose of the object. The shape is going to be encoded as a latent code. So details of that are in the paper. And then this is going to be a controllable humanoid. So we're going to give it this future trajectory of how we want the humanoid to pick up the object and move it. And then the last part is the current humanoid state or proprioception. Right? We need to know what the current state is so that we can figure out what the next actuation should be. Okay, so this model is very hard to learn. If you try to learn it straight from data, well, we couldn't get it to work. Okay. So we take another trick, okay, using another method from ICLR that then developed called Pulse. This is a encoder decoder, let's see, representation that finds a latent representation of the action space or the actuation space. Okay. So what we do is we ask Omnigrasp to give as output actuation in the latent space and not in the full space of the humanoid. Right. It's going to be corrected by the pulse model. There's a prior model that's interject some more actuation information. And then we have the decoder that takes it from the latent space to the full actuation space of the humanoid. Once we have that, we send it to the physics simulator. The physics simulator will roll it out one step, and then we repeat this process. Once the model is learned, we just repeat this process many times, and what it will do is generate a humanoid motion sequence that will pick up an object and then move it however you want it to move it through the air. Right. So here's some examples. Right. So for this robot, we just tell it where the object is in the beginning. We tell it what kind of trajectory we want it to follow once it's grasped it. And then you see a couple of rollouts here for multiple robots. This is showing some examples on the grab data set. There's like 50 objects. It's showing how this policy that's learned in this method can pick up all different kinds of objects and then move it around however we'd like to control it. Right. Same thing for the OakLink dataset. This one has many more objects. That green dot there, that is the trajectory that we're asking the robot to follow once the object's been grasped. Right? You say, okay, I've only seen little objects. What about big objects? And also do big objects. Okay, yeah, so for that one, we don't have any robot demos yet. I guess that's coming soon, maybe. All right. So to wrap up, there are many ways that we can model the body. And really, it depends on, what area of research you want to explore and maybe what kind of applications you have in mind. And there's also many ways that you can model motion. So I hope that through this talk, you get this idea that this sense that there is a big space of solutions, depending on what your representation is, what your motion model is, and depending on what you want to do with that model. So I hope you keep that in mind as you do your own work. Okay, we have 10 minutes, since we have a little bit of time. I'd like to do a short plug for some data sets and benchmarks that are coming out. The first one is the Eagle XL4D dataset. Okay, this is a very big data set, but a portion of the data set that might be really relevant to this crowd is out of the 7 different benchmarks, one of them is this Eagle body and Eagle pose benchmark. It has multiple external cameras and a wearable camera, the Aria glasses. And we've annotated all of the body poses in 3D, well, 2D and in 3D. And we've also annotated all of the hands in both 2D and 3D. So this is the biggest manually annotated 2D, 3D data set. Okay. Literally spent millions of dollars doing this. So I hope that it feeds your research so you don't have to spend those millions. Okay. The other data set that we're working on now is this Harmony 4D data set. So a lot of the multi-human interaction data sets that we have now, there isn't a lot of interaction between the people. So maybe like a kind of slight hugging or like shaking hands. What we try to do is we try to get a data set of people really like hugging tightly or wrestling. We even have like MMA fighters as this part of the data set so that we could begin to kind of push the boundaries in terms of multi-person interaction data sets and methods. And then the last one is if you want to move into this humanoid control area, we have Zen and a group of others have developed this SMPL Olympics benchmark. So I think there are 10 different Olympic events that you can challenge yourself to. And you can bring your humanoid control algorithms here and see how well you do in our SMPL Olympics. All right. All right, with that, thank you very much.
Fun fact, was my PhD advisor, so I've asked him enough questions in my days, but you can ask questions too. Just raise your hand, be loud. We'll take 2 questions, or you can queue up.
Okay. All right. Everybody hear me okay? Yeah. All right. Pretty sure I've got about 3 times more slides than I have time for. So we may pick and choose as we go along. But let's see how we get on here. Great to be invited. Can I get my mouse to work? That's the question. Okay. All right. I'm going to give an overview that sort of connects, this workshop around humans, 3D humans in particular, with sort of the bigger picture of human-oriented computing over actually the last 70 years and into the future. I'm going to talk in particular about us going from internet scale sort of 2D data sets to the future of contextualized AI with 3D egocentric wearable computing and sensing devices. I'm going to talk about how we're going to encode that probably, so that actually AI can get access to your 3D human reality. And then, although Chris has already just given us a quick overview of data sets, I'll go over some more problems that we're sort of looking at together with the new data sets. Okay, let's kick it off. So the big picture. When Alan Turing was first sort of thinking about computing, he was in a world very different from the one we know today. He didn't have 2D graphical user interfaces, let alone the phone in your pocket. And yet, they were inspired by what they saw around them as computing as it was were humans and humans interacting with humans, humans interacting with other scientists in particular to solve problems. And since then what we've had is essentially this guy who came along in 1968, along with a lot of folks from the West Coast of America. And he basically said, well, look, sure, we've got scientific computing, but computing that's going to really amplify humans is this paradigm of interactive computing. And in what's now called the mother of all demos, Doug Engelbach in 1968 introduced us to the first graphical user interface connected with a mouse, networked computing, printers, actually full video streaming. And the descendant of that, which came along shortly in 1973, the Alto, really is the great grandparent of essentially the thing that you have in your pocket today. What you really think of, or what most people on the planet think of as computing, which is internet connected 2D graphical user interfaces in a mobile phone format. Now, that is the first wave of human-oriented computing. It moved from sort of pure scientific programming for the purposes of all sorts of big engineering efforts to essentially everybody being able to be somewhat amplified by a computing device. And, yet our human experience goes far beyond that. Now, luckily, Meta and other companies have been working hard on trying to bridge the gap between the vision of what might have been in the minds of people like Turing and those who were thinking about artificial intelligence, robotics, and other forms of computing, and today. And here's a first example of one such thing going far beyond a 2D screen.
Where am I? Where are you? Where are we? We're not, right? So I mean, this looks, we're surrounded by darkness with ultra realistic things that can feel like we're in the same room. This is really the most incredible thing I've ever seen. I'm sorry, not the first thing. I mean, we have that you did before. Yeah, no, I was coming to the team before that. Even that I thought we choked each other from further distances than we are. I mean, this is just really incredible. I don't know if I can describe it before. It really feels like we're in the same room. Yeah, it feels like the future.
Okay, it feels like the future. That was the Lex Fridman podcast with Mark doing a live social teleportation between 2 parts of America, quite a long way away, and yet feeling as though they were physically co-present. And what the requirements on that were, well, of course, start with the ability to at least capture the humans' personas, their avatars, and then drive them in real time, compress their reality and transmit it over the hundreds of miles between the 2 places they were. And this is really a new generation, what we call the second great wave of human-oriented computing. And it literally hinges on us being able to wear devices like those headsets that Lex has on here. Who here actually saw that podcast online? Okay, hopefully you connect your own work in 3D humans and where the future of avatars may go to solve social teleportation. But there's a lot more to that, essentially to humans and our 3D human potential in computing than just immersive codec avatars. And as the introduction noted, a few of them are sort of really starting to get interesting for us. So social teleportation is one. It's starting to become possible. Mixed and augmented reality, so virtual objects, very interesting to be able to just program reality in software and have it sort of show up in reality. Robotics, and the one that really my teams have been working on now for nearly a decade, which is human AI interfaces. Now, during also around the time that he was developing sort of the first computing paradigms, said what we really want is a machine that can learn from experience. Now, it's hard to think about what he could have meant by that other than human experience, because, as I say, there was no internet, there was no other kind of digital experience. So all there were humans interacting in the world, learning, and essentially, becoming smart from it. And I guess between then and now, well, I guess AI is now here. So something happened in the process that allowed us to gain the experience that humans do to provide us with ChatGPT and all those lovely things that we've been playing with over the last couple of years. So AI is here. Well, what on earth does that mean? Well, we really mean chatbots are here, these disembodied AI that we interact with through text alone. And, certainly coming multimodal AI, and we're going to talk a bit about that. But something from that text-based AI is clearly missing. I wonder who can think about what it is if you've interacted with these things before. It's clearly your real-life context. So for you to interact with an AI today, like a chatbot, you literally have to tell it everything about what's going on. You have to literally type it in. If you're looking to get access to new versions of multimodal AI, maybe you can put a small video clip in there. But there's a new generation of AI coming, which is based on AI plus wearables. So Ray-Ban from Meta has essentially a generation where taking a photograph together with audio allows you to ask questions from your embodied perspective. But there's lots of other devices, those things like pendants that record your reality whilst you're speaking and chatting to others, other devices that are perhaps not doing so well as a first generation to try and surpass mobile phones, but they basically have cameras and microphone arrays, and they interact with you in your reality rather than through 2D screens. I think we've lost the microphone. Okay, I'll keep going, although my voice is not very loud. Okay. Yeah. Okay. Oh, we're back. You can hear me. So I don't know what that was. We'll keep going. Okay. So Ray-Ban Meta is certainly another generation, very different from the immersive VR and mixed reality headsets that the social teleportation experiments are being done with. But they get it closer to reality. They get it closer to what could matter for AI to interact with you everywhere you are, everywhere you go. Okay, part two. From internet scale AI to contextual AI. So contextual AI, simply stated, is your context, meaning the physical and digital reality that you have, together with some sort of a reasoning engine. And I'm going to state that basically I think that side of AI, that is to say something like ChatGPT-4 and things that will come later, agentic AI, things that have a better closed loop goal-oriented AI, they're fine. Actually, our big problem today is getting that context. Getting your physical context to the AI is the real problem that we need to solve. Now, can multimodal LLMs get us there? There's a nice report here from, just last year. And of course, a lot has been done since then. But realistically, I'm going to state as well that no, multimodal LLMs are not going to get us there, because the way that they are currently being positioned is via raw data being tokenized via something like a transformer and then passed in a sort of a joint encoding to something like an autoregressive model. And we're going to see shortly what the problem with that is. In fact, there's two problems. There's the data and the compute problem. So if we're going to try and get our human context to machines, then we have to confront the fact that there's data that you need to be able to collect for training. And we saw just from Chris's talk earlier that a lot of people are starting to turn to simulation data sets to try and get 3D data, because otherwise, where's it going to come from? There isn't an equivalent of photographic, scaled data that there was for video clips and photos on social media for your 3D data. let alone where you're looking and what you're saying and what you're interacting with in 3D. The data doesn't exist for training. And even if it did, you still need to get the data from devices like that pair of Ray-Ban Meta in an efficient enough way so it can be computed with, which brings us to compute. We're going to see in a second just how big egocentric 3D data sets get. And, whilst you might be able to train with like, thousands of A100s in a data center, even if you could get the data, actually computing with it in real time on those mobile wearable devices is another thing altogether. So this is the big problem. There's already a problem even for internet scale data today that looks a bit like this, but actually when it comes to real-time contextualized AI, it's actually a completely different order of magnitude altogether. Which brings me to always-on contextual AI. So today we might think of contextualized AI as simply, I ask a query in the moment and then suddenly I get an answer. But realistically, for AI to be useful, it's going to have to be always on. It may not be doing anything, but it's there observing, understanding what you're doing, recording some sort of a history of what's been going on so that it can be used later on. So how are we going to get there? Well, as Chris and others will probably show in today's workshop, we've been doing Project Aria. Project Aria is a first generation glasses device designed purely for contextualized AI. It has a ton of sensors that we'll have a look at. And the general mission is to essentially accelerate everybody doing work in real world humans. So projectaria.com is where you can go and have a look, and those devices are free for industry and academia to be able to use and collect their own data sets with. The sort of data sets are what we call egocentric. So because they're glasses, they are from the person's point of view, interacting with reality. And to date, thousands of hours of data sets have been generated by hundreds of universities, including the Ego 4D effort that we're part of together with Chris and team. Okay, so Aria is a splendid device, 7 microphones, because you live in a 3D audio environment, eye tracking, together with SLAM cameras and an egocentric RGB camera. There's a lot of data that comes from these devices, which is part of the potential for doing research with this, but also part of the challenge. We'd like to be able to capture data through an entire person's day. So, for example, from waking up as a glasses wearer, first thing I do is actually put my glasses on. I might read the news. I might do several other things, including going outside, doing activities, interacting with digital devices. But each one of those events has itself a sort of a breakdown of very micro activities. And the question is, to what level of granularity can we really record our 3D interaction with reality? If I take just an example of doing some exercise, here's sort of like me pretending to do a headstand or a handstand. My foot might move forward by a tiny bit. I might look where I'm about to put my hand. My heart rate, which is an important signal, might start to elevate. My breathing might start to increase. And eventually I might fall over and not be successful at doing a handstand. But the point is, capturing it would require micro precision of my hand placement and even what my feet are doing, if you really wanted to understand what it was for me to do it. It's not just this visual exterior. There's things going on in my body that create me that is a 3D human. Now, as a Project Aria device, we have essentially a lot of data. It looks a bit like this. These SLAM cameras allow us to estimate head pose very accurately and hand tracking, the RGB camera, eye-facing cameras, and so on. Together, that data, even when compressed, is on the order of a terabyte per person per day, for an 8-hour day. Now think about that in terms of the scale of data sets that you might be used to. This is just one person, just one day. How diverse can that be relative to internet scale data sets where we're used to 20 or more years worth of data over millions of users, giving diverse perspectives on if it's this photo and it's this summary. Well, that's quite a valuable thing at billions of images. But you can have billions of frames in a year, and it might be pretty much the same depending on your particular lifestyle. In fact, when thinking about interactive data sets of people interacting with Aria, those data sets start to basically blossom at around 30-odd petabytes just for 1 year. So think about collecting this data and then think about uncompressing it inside of a GPU center where you're going to do some sort of error from some sort of neural network. It's actually infeasible to collect this data and then process it at the kind of diverse scales that we know that our AI models today need. So that's certainly a problem. Generally speaking, it's just not feasible. You can't collect this kind of data and process with it, even though that is the new source of data, the new sources of data for training AI on. So can we compress it? Well, I put it to you that we really don't need all of that raw data. Essentially, we can think of it in terms of, from your perspective, what is it that's important for you to be able to get done what you did? And that's an interesting and very different question from sort of like the complete manifold of data that might be observable of you exteriorly or even from an egocentric perspective. So what did you hear that caused you to have an action? What did you say that caused some change in reality? What did you interact with? Where are you? And, you know, is the state of you changing? Now, this is where we get basically to the heart of 3D humans and really being able to capture the state and the change of state over time very effectively, very compressively. In fact, who can have an estimate of something which, although we mostly think of it in terms of digital data today, who has an estimate here of how many bytes of data per day for everything in a day where you're writing, whether that's with a pen or with a keyboard, reading, whether that's, you know, signs in digital or, you know, or analog, everything you've said and spoken, everything you've heard. Who here has a guess that they want to give for how much data that is per day? I'll pretend to say that there's a prize if you can get it within an order of magnitude. Anybody? Go for it.
5 gigabytes.
5 gigabytes. Great answer, off by a few orders of magnitude. That is about a megabyte of data per day. Think about that relative to those ARIA data sets that include the raw microphone data. Okay, what about things that are a bit more permissive in terms of interpretation? Everything you've touched, everything you've seen, everything you have seen, everything and everywhere your body is, the entire body pose. Go with 100 joint positions per 60 FPS. Who has an estimate of what that number is? Ten megs. I'm just going to leave a question mark there. We can talk about it afterwards. I think it's about 10 megabytes. And it's interesting to think about that, but I'll show you something at the end if I have time about foveated vision and just how compressive it actually is. Think about it in this way. Human eyes have a fovea. That fovea is where your high resolution, essentially 20/20 vision exists. It only exists within about 2 degrees field of view. Humans fixate at a rate of about 2 to 3 points per second. When you're reading, you might go a bit faster. Depends how much of a speed reader you are. Otherwise, your eyes are kind of going tick, 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 2 to 3 times a second. They don't go ever more than 8 times a second. That's the rate at which massive changes are going on, so that you choose to actually saccade somewhere to put your high resolution, small 2-degree field of view at the point of information. It's much lower rate than 60 FPS, for example. And that 2-degree field of view is much smaller field of view than 120 degrees field of view, which is what you think you perceive. But actually, you don't really observe that. That is an illusion created by your brain from the model it is generating. Okay, so can we represent all of that context? Well, if you start to see that kind of like megabytes per second are quite a lot smaller than the raw data, then the potential answer is yes. We just have to be judicious in what we're going to encode. So encoding reality. So my teams over the last sort of 10 years have been building very efficient encoders, mostly to enable to light up in the short term these kind of new mixed reality headsets. They need to know where your head is. They need to know what surfaces are in the environment. They need to know what your hands are doing. What we see here is what we call a live map. This is essentially a map of a person's environment that gets created on the fly from a pair of ARIA glasses. From the data streaming in, there's no actual data that needs to be stored in principle. The model gets generated. And from this map and the interaction of the human with the environment, what we end up with is an incredibly compressed state of reality. Now, it's not photorealistic, but like I say, it's questionable what the photons are that you do need to record as to what you actually perceive to actually get your job done. For example, reading certainly needs high resolution vision, but most of the rest of your tasks don't need that sort of resolution. So here we have a 3D predictive model of reality. We break it down in terms of the environment model. That's in terms of external maps. If you have them, you should use them. This building, for example, has external maps. So when you're in here, if you had a location system that was locked to this part of the building, you'd know you were in here. And when you exit here, that state change might be very informative to an AI that really wants to know what you might be doing in a particular place. As we move up the stack, we get basically finer grained 3D surface information that goes from physical surfaces through to semantic surfaces or building structures. It's important to know what a floor and a wall and a door is, because they have the very different sorts of functions in our human 3D reality. The static index is everything that essentially is not nailed down, but ultimately, doesn't move a lot. And then the stuff that we're really interested in here, which is this human state and the dynamic index. Humans move the world forward. The reason why it changes is because humans change it. It doesn't suddenly change overnight. In fact, this room with all of you in is as complex as it is because one at a time you entered this room, possibly moved the chair a little bit, fidgeted with some of your equipment, and are now looking in this direction. This entire complex scene is comprised of your small changes of state since you entered this environment. You know, and afterwards, when this conference is done and it's returned to an empty room, it will have been done at the rate of change of a human interacting with the environment at a very few number of bytes per second. Think about that compression. So underlying all of our systems are what we call spatial AI. Spatial AI starts with being able to get exquisitely accurate head pose from those glasses devices. And this is a problem we've had to solve to enable very low power tracking for mixed reality and other virtual reality devices. The value of this is that it provides a space-time frame of reference in which all other information can be anchored. And that's going to allow us to have some very high performance traits for other sorts of systems like human body pose estimation. When you've got that sort of pose of the device and you've been able to collect sort of point clouds, you can start to label those point clouds just by splatting them with semantic information from the latest and greatest semantic scene understanding systems. That's also very useful context. You can't walk through walls. You have to walk on the floor. So if you can label those things, then constraining where your body is and what might actually happen becomes very doable. Which brings us to human state, which really is the main actor in this entire system. So essentially what we want to get is a complete body model being decoded and effectively, if we can, predicted into the future, all from just a pair of glasses. Now, the team has been working, over the last 3 years to be able to build such a system that allows us to get a brand new data set, what we call Neria, and that's just it's being released. It's on the web page now if you Google Neria. Essentially, this is the world's first fully metric in the wild data set that allows us to start to train full body decoding from just glasses. I'm going to take you through what's in it. I'm very excited about this data set. So we had a lot of wearers, fully consented, wear very strange suits that for some reason we didn't ask them to wear normal clothes over. They could have, and that would have been delightful next time. Otherwise, that literally is what they were looking like when they were doing these data sets. It comprises an ARIA device, which is glasses, with very high accuracy time synchronization boxes to connect to the XSense suit, which is an inertial suit that they wore. And we also took ARIA, the glasses, and put them into 2 wristbands so that we could run the same SLAM stack that's running on the glasses on the wristbands so that we have metric wrist pose together with the same frame of reference as the head. So this is sort of like really ground truthing for the human without, for example, having to be in a mocap space. It also includes eye tracking, of course, which is very useful. We'll see that a bit later on. Okay, so just to run through what's basically there, we've got the ARIA with its cameras, its IMUs, and its eye tracking, its audio that we also record. And we run 6-stop pose estimation on it and on the wrists. And then we fit a skeleton model into the aligned frames of reference of the head. So we anchor the body to the head pose. Actually, you can see here, Lingley, the lead researcher, you'll see some nice cycling data sets in a bit. We retarget it to a full human body mesh and optimize it with respect to the full world frame of reference coordinates. We also record for every single data set a third-person perspective from a second ARIA wearer that is also in the same frame of reference so that we have a full third-person point of view on the person doing any activities, and that's very valuable as well. It is the largest metric data set of human motion in the world by far. And it has some very nice properties. It's interesting to think about, how far your wrists move. Well, in this data set here, over the sort of like 1,200 sequences, we've got about 1,000 kilometers of wrist motion, which, if you think about it relative to the head trajectory, it is about right. But it's interesting to think if you ever wondered like how much further your wrists move than your head in the world. Well, we've kind of got a good estimate now of what that is. It also comes with 136 hours of narration. So as people are doing activities, then we've also got basically what it is that they're doing in narrated form. As I say, it's in a frame of reference that's all calibrated. So we have metric poses. And for example, in this case, for the 47 Airbnbs that we used, each sequence being around 4 to 15 hours for each space, then we've got the head, the wrists, and also, of course, the full retargeted body. but they're all in the right frame of reference. So we might have several people in one Airbnb. They're all in the same frame of reference. So if they were in the kitchen, doing things in the kitchen, then the 13th sequence is also in that same kitchen. It's very useful from a point of view of the data and things that are going on in those different environments to be world locked, essentially. We've got very large scale indoor to outdoor data sets. So people walking and doing hiking through woods whilst going into multi-story buildings. And I think one of the most delightful things is that when you see some of the data sets, from just the body poses alone, it's very clear to humans what's going on with no more data. So if you have a look at this one, which is floor is lava, just at the bottom in the middle. Who's ever played floor is lava with their kids? If you ever played this, this is a great game. You have to basically pretend that the entire floor is either on fire or hot lava, and they have to move their way around the environment without touching the floor. Now, for anyone who's played it, they would probably be able to guess that that's what's going on simply by looking at that image without knowing the text. And that's interesting because it proves this kind of concept that we all know intuitively, which is the body pose has a massive amount of information. In comparison, it's highly compressed relative to the raw data. Okay, so you would really check out that data set for a new generation of 3D humans. Now, we've used that data set, and in a new piece of work, HMD2, which should be released soon, we have trained a diffusion model to go directly from the ARIA glasses, so no wrist device, no bodysuit, only ARIA glasses, to decode an entire body model. And this was extremely surprising to me because, of course, the ARIA glasses can't have a complete view of your body. But it turns out that from connecting just the head pose, which is a very high resolution SLAM pose from the glasses, which of course encodes where your head must be, together with just a clip embedding from the RGB camera, and then training a diffusion model based on essentially the ground truth to diffuse over a few seconds worth of data, then you can decode an entire body pose. And this leads to some really interesting new insights in sort of like predictive models for humans. So what you see here is Lingmi actually walking around one of our labs, and the decoding that's going on is exactly just from the raw ARIA data, from first of all decoding into head pose, and then also taking the RGB camera, doing a clip embedding, and using those two joint encodings together with the diffusion model. What you'll see is, of course, the distribution over the full body. Because there is uncertainty there, and that's the point of these models. It's a sample, it's a generative model. So if we constrain it further, for example, there's no actual hand tracking being used here, then we could collapse that distribution. If we use more of the information about the environment, for example, when a person is sitting down, that their legs won't just swing around, then of course we'd be able to constrain that further. But I really enjoy seeing the full distribution, almost like Neo in the Matrix and all the possible things that he might be about to do. One of my favorite sequences is in cycling. Again, there's no concept here of cycling other than it's in the data, and that indeed the model's been able to learn what it is to cycle and decode. So this sort of, I think, decoding a full body pose is going to be incredibly valuable, given it only comes from a single pair of ARIA glasses. I see our audio's gone again. Brings me to the final thing. Check. Almost. Check. Yeah, we're back. Okay, the new data sets. Well, the new data sets are really extraordinary. As we saw, the Ego4D one includes a lot of the kinds of ground truthing that come from ARIA, but also external extrinsic poses. But one of the things we're most interested in are data sets that start to deal with eye tracking. Here you can see the segment anything model being used in conjunction with ARIA to be able to essentially just highlight where the person might be looking. These data sets of sort of full 3D bodies together with where you're looking are going to lead to a very new generation of both problem definition and also, potential solution, i.e., can I predict where a person is going to interact next? Well, in case you didn't know, you almost certainly have to look before you touch something. In fact, for example, simply walking out of a door, you may have looked at the door 30 seconds prior to you walking in the direction of the door. Think about the predictive nature of the data that's starting to be collected and how actually small it is compared to raw data. I might not need the raw eye tracking. I might not need anything other than just the gaze in 3D space together with a model of the environment. And I might be able to predict exactly 30 seconds ahead of time what's going to happen next. You'll see it in some of these data sets here where people essentially are interacting with small pieces, with doors. They always look before they touch. As Chris was showing, the Ego 4D dataset is a real treasure trove. Lots of good stuff in there. Go and take a look at it. It is the biggest overall multimodal dataset that's been collected to date. And I think I'll just leave us with this one other area, which is really the activity decoding, given eye tracking, just sort of like wet the whistle of what you could think of. Well, people aren't really used to thinking about eye tracking because there weren't any devices to capture it with, whereas Aria, of course, has it for the first time in glasses form factor. And so the question is, how could we trivially incorporate eye tracking into something like a visual LLM? And another project from our team tries to do that in the simplest way possible. It basically says, okay, we could do some sort of a fancy encoder, but all we'll do is we'll simply tell the LLM in plain text where in the image roughly you're looking, literally the pixel location, and associate that in text with the actual textual encoding that comes from the image or video encoder. And the result of that is kind of startling. On the Ego 4D datasets, for example, we see here decoding of essentially what's going on. And on the left, you can see here, without eye tracking, the system essentially just assuming that the person must be doing something with a bike. Whereas when you incorporate eye tracking, you get this fine granularity. Another good example with cooking, here it assumes somebody is cutting an avocado. There isn't even an avocado in that scene. Whereas when you include eye tracking, it understands you're cutting an olive. Think about how fine-grained that is. Now, the reason why I'm showing these is because it's not entirely clear that we're going to get super fine-grained 3D data from hands interacting with objects. There are occlusion problems. But from the context and where you're looking, then it might be sufficient to start to decode incredibly fine-grained interactions. Here's another example here where you see that the gaze stays with the objects rather than just the entire scene kind of being interpreted. So on the left, turns the heat down. Well, it's plausible. And on the right, pouring the egg into the skillet, far more accurate. Finally, as I was saying, you might not even need the actual external facing cameras. Here, what we see is on the left, from the image and the text encoder, the assumption that the person is placing their right hand on the test manual on the table. Whereas on the right-hand side, then we can see reading the instruction manual on the table. Now, the thing is, there's a lot of literature that shows that when you understand human gaze, then actually there are patterns in the gaze alone without looking at what you're actually looking at. From reading, for example, to navigating, to searching for a thing, to trying to make eye contact with someone. Each of these have signatures in just the raw 3D eye pose, which doesn't require you necessarily to look at the external data. Okay, I think I'm out of time, so I shall leave it here and simply state that there are a lot of new problems. And if you're interested, do find me later and do come along to the other related egocentric vision workshops today and tomorrow. Thanks very much.
Any questions? I have one. So I feel one of the superpowers of Aria is the calibrated cameras you get. Do you see a world where we can do it on commercial devices, commercial wearable, or phones? And what are your thoughts?
Yeah, well, I think, certainly we built Aria several years in advance of the products that we're building. And exactly these kinds of encodings that are very high resolution, high precision, but very low power, for example, 3D pose and point cloud decimation are absolutely at the heart of what is going into commercial devices. Of course, like things like Quest 3 and so on already have a lot of this built in, but they're not in glasses form factor. So we're just at the cusp of the kind of Aria technologies being made into products, which is very exciting because it'll go far beyond the kind of current generation of just cameras on the head.
Yeah, we have one there.
How many megabytes is project Neria?
Oh, wow. Lots of gigabytes. Actually, it's just gone live on the Project Aria website. So you can take a look. You don't have to download all of the data. But yeah, it is, it's right up there in the terabytes.
Okay, yeah.
I have a question about this is really to make it work that the Aria like full new technology. I was worried about the future, how it would be like I know that for mainly consumers, a lot of people be worried about having to find monthly everything they're doing. But do you think there's a way to kind of bridge the gap between
Yeah, this is absolutely vital. So you may notice it's very subtle unless you're in this space, but all ARIA data that gets processed has bystander privacy by default, which means all bystanders' faces are blurred, all number plates are blurred. We're also blurring things like phone screens and various other sorts of data that is like very, very much sensitive if it got recorded for data sets. Now, the question is slightly different, which is, well, what about my privacy as a wearer? So what we've said is this: if it's my data and I'm consenting to my data to be provided to my AI, like my emails or, literally when I type to an AI, then I am in control of that. And so your own data is yours to consent to, but that means capturing your data, what I say, what I look at, what I interact with. And that's why it's so important to solve these encoding problems and move as quickly as possible away from just raw data. Raw egocentric data has a lot of problems associated with bystander privacy. And so I think the key is this: if we accept that you are in control of your digital domain data, like your email, and you have to cross that chasm, your bank account details and so on, today we are relatively at ease with the fact that these kind of data is available for use for search or analysis and so on. It would be a completely different thing if I was to start to turn up the things that I say, the things that I interact in your sequences. And so the separation here is that privacy means essentially for the bystander by default, but certainly for me personally, I'm allowed to consent into my AI having access to what I want it to. And that's the real challenge, is to sort of understand how to encode what it is that I'm saying, doing, seeing, hearing, and so on, versus what it is that might be going on throughout the rest of the environment. Hopefully that makes sense.
All right. Let's keep the questions at the end of the time. Let's thank Richard again. Thank you so much. Our next speaker is from Computer Science Department at Stanford.
Thanks for the introduction. My name is Karen Liu. For those who might know me, you probably know that I'm not in computer vision. My research background is in computer graphics and robotics, so it's absolutely a pleasure to be invited to come to CVPR to talk about my favorite topics, 3D human motion synthesis. So this is really important topic for character animation, because if we're able to synthesize realistic human movements, then we can directly improve the fidelity of our digital agents in a lot of different applications across different virtual worlds, AR, VR, films, games. It's also study human motion, 3D human motion is also very important for robotics, because if we know how to use our own body, own movement to demonstrate to the robot, maybe the robot can learn better, learn how to move like us, learn how to interact with us. So my research has been working on these two different fields, robotics and character animation. And literally half of my lab is focusing on this little digital characters who knows how to move its own body, but it doesn't really have a brain to make a decision. So instead, oftentimes we rely on human intelligence. We call this a user or an animators that can make decision for these little characters. So we have this character lives in the virtual world, but its brain actually lives in the physical world, right? And we call this animation. The other part of my lab is doing something exactly the opposite. We build a physical body, which is driven by a virtual brain. And this virtual brain, in the past, we call it planning and control. Today, we call it machine learning or AI. But I wanted to just to differentiate a little bit from the general AI. I think a more precise term for that would be embodied intelligence. And it's precisely this notion of embodied intelligence that give us a lot of new challenges and new opportunity for 3D human motion synthesis. So imagine that now with the large models becomes a common commodity. We can instantly upgrade our characters, our digital agent, to be able to make intelligent decision based on its own observation and reasoning about this virtual world. So this character now is able to see the world, to listen to the world, to speak, to touch, and make a decision based on these multimodal observations. And to build this AI-enabled digital agents, we need to rethink a lot of things, just like the way we think about robotics. We need to think about how we can capture human motion data for embodied intelligence and build a train a model, a large and multimodal models for generating human motion, and how we can adapt these pre-trained new, I call large motion models for our embodied applications. So today I'm going to just focus on embodied data. Our labs are working on all three different fronts, but embodied data seems like it's a going theme for a previous speaker as well. So I'm going to talk a little bit more on how we collect data. But again, before we can think about what kind of data we should collect, we have to think about what models we want to build, right? Because data collection, as you heard from Richard, is expensive, and storing those data is, it is not trivial. So we need to be able to be very careful about collecting data. First, by thinking about what models we want to build. All right, so in computer graphics, the models we usually have is a model that take as input the commands from the animators or from some kind of low-level control procedures and then output will be a trajectory of a 3D poses. So nowadays, with the generative AI, generative modeling, we start to think about motion trajectory of poses as a target distribution we want to hit. So ideally, we want to build a generative model that can start from a random seed, and then you can generate infinitely long random motions. But it's similar to the real human motion distribution. But the most interesting thing is that when you condition this model on something that's useful, for example, what the character sees, what the character hears, what the character remembers, then this model becomes really interesting and powerful. And if you have a data, let's say label data, medical label data, then you can train a model that can do some kind of predictive outcomes of a particular medical intervention, right? If you have biomarkers, you have anatomical properties, this becomes some really useful model that can directly have application in healthcare. So that's great. We want to build a model in general that has multimodal observations paired with actions. That's the kind of model we want to build. Let's collect some data for that. When you go back to data collection, the gold standard data collection for 3D human motion today is still this kind of optical-based motion capture system. And this system is designed for collecting the data and collecting the action and the action alone, not the observation the subject performs. So in other words, we have a motion capture pipeline that allow us to collect proprioception, but not other type of modalities in perception, like vision or tactile. So that's something we need to address, the problem number one, when we collect data. What about other requirements for building these motion models? Well, I think someone mentioned earlier, Chris probably, that we want sometimes not just the kinematic motion, kinematic information like 3D poses. For a lot of applications in robotics, in ergonomics, in healthcare, we want something that's in the dynamic domain. We want to be able to understand how you give what kind of dynamic information that give rise to this kinematic information that we can observe. So maybe we need the contact forces, we need joint torques, we need muscle activation. So that's kind of data we want to. And sadly, today, the kind of data collection pipeline only allows us to collect kinematic data, but we want both kinematic and dynamics information. All right, so that's the problem number 2. Now, finally, we it's great to have a data set that has multimodal observations and also dynamics along with the kinematics. But essentially, we need the data to be data set to be very large, both in terms of quantity and diversity. This means that we need to have a way to capture data in the wild around the clock, right? And that's and not only that, we have to maintain the high accuracy, high diversity, multimodality, and with both kinematics and dynamics. Okay, so that's what I envision the kind of a data set we need in the future. How do we achieve that? Step number 1, let's figure out how we can acquire contextual motion. Sadly, we don't have a way to collect contextual motion today, but that's okay. We can reinvent the way we motion capture the world. And this is exactly what this project is about. Can we capture human movements in a highly contextual environment, along with the corresponding egocentric observation? And that's very much echoes what Richard just said. We need to be able to have those observations being captured along with an action itself. So for example, if you want to capture someone, reaching into this very cluttered environment, like behind the toilet, trying to pick up something, how do we do that? And we want the motion to be really high quality, like the motion, the optical-based motion capture system quality. More importantly, we want to have an egocentric view that's paired with the actions. So this will give us a chance to answer a question not only what the people are doing, but why the person is doing what, the performing that task. So idea is to use mocap system, but quickly you realize it's not possible. You first have to build this whole set, the bathroom set in your lab, and also there's a lot of occlusion if you do so. So we come up with an idea to combine the optical-based mocap system with the virtual reality. And the idea is to let the subject wears this headset. This is a Quest, and we stream the virtual scene into the headset while the person is being motion captured in an occlusion-free environment. So this is really what our lab right here. And then we then ask the subject to do something interesting, like reach into the closet to search for a particular toy, or go, pick up a pencil underneath the table. And then so this is one session that we recorded in our lab. So this person is trying to pick up something behind the chair, but the chair, the entire, the scene is in the virtual world. Okay, so this really gives a way to kind of create an illusion for the subject, such that the subject can, perform a very trivial reaching motion in a very realistic way. And we collect 10 hours of the data with 9 different scenes. This is a collaboration with Meta, using their Habitat virtual environment. And this way we can really quickly create many different diverse scenes to collect data like that. Okay, so you ask, well, this is interesting, but what about physical contacts with the world, right? Because that's what we do a big percentage of our waking hours. How can we collect motions with the physical contacts, especially object manipulation? And this is what we do in this recent paper submitted, accepted at RSS. So the goal is to collect dexterous manipulation in the wild. And this is targeted for robotics, because we want to be able to teach robot dexterous multi-finger robot hands to do something similar to to reach human level dexterity. So there are different ways you can collect, hand object manipulation data. One way is just go back to motion capture lab. Actually, Michael Black's lab has done this really nice work where you collect very detailed hand manipulation with the object along with the object motion. But this is a little bit hard because you have to do that in the lab setting. Our goal is really be able to just go out to different places in the world and collect the data together with object motion, hand and object motion. And another prior work is to use VR headset to do that because we know VR headset has a very good hand tracking already. But this usually has, occlusion issue and also limited field of view. So we build a new data capture system. We call it DexCap, as in dexterity capture, as opposed to motion capture. So DexCap is a portable system, as you can see. And the goal is that, it's very easy to put together. Everybody can just, look at our video and then, create a system like that. And then you can start collecting data. So DexCap contains a pair of gloves, motion capture gloves. This is the IMU-based gloves, SLAM plus IMU-based gloves, so that we are not subject to the occlusion issues. And it also has an RGBD cameras that wears around the chest so that you can collect the information of the environment. And in addition to that, we have the 2 SLAM IMU cameras that's seated on the wrist to localize the wrist pose, 6D pose, so that we know because the gloves only give you the finger information. All right, so before we start collecting data, we first need to calibrate that. And we have this 3D printed cradle where you just put 3 cameras on there and you can just automatically calibrate that. And now you can start moving the blue and the green cameras to your wrist, where the location, the cameras are starting localizing already, and then you start recording your data. So this is a quick test to show that how important it is to have a SLAM enabled pose tracking. You can see that my students moving the cameras around, and it's doing localization at the same time, and eventually it can reach the exactly same location. But if you just use IMU-based tracking, which we did for a few other projects, there is just a significant drift problem that has to be handled. Okay. All right. So once we have this data set, the hardware, we can go out and start collecting data to build our data set. You can see channels moving around just to calibrate all 3 cameras at the same time. And now the environment, the motion of the environment or the object is also being collected simultaneously in the 3D point cloud representation. And this way we can collect a lot of data very easily and very quickly. All right, so once you collect a whole bunch of the data, what do you do next? We need to train a policy for the robots, right? For the robot hands. And we actually just do something very simple for this project. The first thing you need to do is to retarget your human hand motion to the robot hands. Robot hands are quite different from human hands, even though those are considered dexterous hands, multi-finger dexterous robot hands. But it only has 4 fingers, and it's roughly 1.5 times bigger than human hands. So we had to carefully target the fingertips location in 3D to the robots. And we also have to target the action space, but action space in this case is just target pose. So essentially it's the same retargeting method. And finally, we train a diffusion policy using behavior cloning, and that's very straightforward. And surprisingly, it kind of just works. Once you train this policy, you just go to the robots, give the robots this brand, this policy, along with the cameras that you when we work with the robots, only the first camera, the RGBD camera is used. And now we can quickly, show that the 0 shot, the policy can just work with the dual robot arms. And it's a little bit slow because I want to show that without speeding up the video. But now you can see that my students start moving the target location and initial location of the objects. You can see that robot is still able to achieve the task. Okay. So this is a simple task, and then we start to collect more data. Maybe the whole idea of this is a portable system. You can go anywhere, collect all different kind of objects in different environments. So again, Chen walks around in the in our basement in Gates in Stanford, Gates building in Stanford, and just start collecting data without a lot of additional calibration. Okay, so we something like that. He repeated it many times. We collect 6 different objects, and now we want to show that we can use the 6 objects packing task and generalize that to unseen objects with the same packing task. And this is all 0-shot training. Okay, all right. What about long horizon task? We also try something more challenging. In this case, my student Chen is trying to demonstrate how to prepare brewing teas. We didn't go all the way until the end, but at the very beginning, you need to twist open the bottle, the tea bottle. You need to use the tweezer to get the tea leaves out. That part we're trying to get a robot to do. And turn out that this is not as easy as the other tasks. The main reason is because we don't have haptic information. So sometimes the twist, the opening is a little bit hard to succeed. But still, most of the tasks were, scenario we try, we're able to accomplish the tasks. All right. Okay. So we have, so this is our RSS paper. We'll present it in 2 weeks. If you need more information, definitely go to the website. You can find the paper, the source code, and very soon we'll have a video because this idea of open hardware is something that our lab fully embraces. We want to be able to build something and other people can repeat that process as well, so that it can really help us collect more data and then share the data with the community. Okay, so that's just step number 1, and I'm gonna have to speed out a little bit. Step number 2, how do we go from kinematics to dynamics? And that's something that's very, very important if you're working in biomechanics, if you're really trying to think to what end we are going, right, as a community. Why do we care about human motion? Eventually, we want this human motion has some real application that can improve the well-being of humans. So dynamics is really important step toward that. We don't have a way to collect dynamic data, but hundreds of biomechanics labs in the world do. Okay, so remember, by biodynamics, what I meant was basically the force and torques that give rise to the kinematic information. So we know most of the labs, biomechanics lab, has this kind of devices to capture quantum reaction forces. That's great. The problem is that they collect a lot of data without sharing with the community, and there are reasons for that. One reason is because they usually have very specific experiments. They collect data for exactly that setting. And another problem is that the data are really heterogeneous. There's no way that you can just directly plug in or download the data and use machine learning toolchains to build models, right? So we want to change that. And our idea is to, our solution is what we call App Biomechanics. It's a web-based tool. It's a very simple idea. It's just, a web-based tool that everybody can use. You give us your data, and then we will build a digital twin for you and turn your raw motion capture data into dynamics information, add dynamics information to your raw motion capture data, right? So a lot of things that, like AMAS data, for example, you can just, try that and then get a joint torques out of it. So how does that help with the data sharing? Well, currently, this is kind of landscape we're facing. We have some public data sets, but a lot more private data sets that are not shared with the public. So App Biomechanics can expedite the data processing for users, and that means that researchers can now collect more data easily and more quickly. And App Biomechanics handles this entire data post-processing pipeline, which means that all the data we get at the end, they are harmonized, they are machine learning ready. And in order to help promote data sharing, we let everybody use this App Biomechanics web tools free of charge in exchange for their consent to donate the data. So this way we can really aggregate this data collection effort from every biomechanics lab, every studio to create this unprecedentedly large data set that has both kinematic and dynamic information in there. So this is something that we process. You can see that we get very accurate contact forces as well as a huge diversity of a different kind of the data. So at Biomechanics right now, so this is a data collection, but we actually don't collect data. We just help people process data and then let them donate their data to us. So now we have more than 70 hours of the data, a lot of frames, and with perfectly or near perfectly matched kinematic and dynamic data, along with a scaled digital twin skeletons for the data. Okay. So speed out a little bit. We released at Biomechanics web tools about a year ago. Now we have collect more than 800 gigabytes of the data, and there are a lot of biomechanic labs from across the world, all pull together their data collection effort and create this data set. And if you have a data set, you have a motion capture data set, just kinematic data, just give it a try. It's really simple. Go to the website. You just upload your data, wait for a few minutes. You will get your digital twin back along with the joint torques and ground reaction forces. Okay, so this is what biomechanics can give us. Why are we doing that, really? The way we think about biomechanics is that this is really a seed data set. What we want to be able to do, use this data, this nicely paired data set prepared by the biomechanics experts to train a model such that in the future, we do not need dynamics data being collected all the time anymore. So we want to build a model that can predict from kinematics to dynamics. So joint torque is what we usually want, right? Because that gives you, that's what biomechanics people, ergonomics researchers usually want. But it's really hard to predict that. Instead, we want to predict external forces. And the good thing is that if you can predict the external forces, it's actually analytically, there's an analytical way you can go back to joint torque. So how do we predict that? Since we don't have a lot of time, I will just skim over this. That the idea is really simple. Go back to Lagrangian dynamics, to the Newtonian physics, and you look at this equation. What do you know? What don't you know? And how do you figure out? And then quickly you realize that this Jacobian right there is most of the time is low rank because you have a multiple contacts. If you have a single contact, it's not a problem. Multiple contact, you will have to deal with one-to-many mapping problem. And how do you deal with one-to-many mapping? We have so many tools today to do that, right? For example, you can build a diffusion model for that, right? So diffusion model has been mentioned a few times, so I'm not going to repeat that. But the idea is think about your data as like an image, right? This is like an image, 2D image. You have joint angles, those are kinematic information you have, joint velocity. And then there's also external forces, that's what you want to predict. But in your training set, you have all three of them, right? So you train a diffusion model, and then later on you do it in painting to get from the green to the teal color, or from the kinematics to the dynamics. Okay, so that's the basic idea. And this is what we end up being able to predict. If you give us some kinematic motion, we can predict ground reaction force. And once you have a ground reaction force, you go to inverse dynamics, and that will give you a joint torque. That's what most of the biomechanics people want. All right, so I do a super quick, interesting, I'm just gonna skip this because I have step 3. So the step 3 is actually something that a lot of people have to talk about. So I guess I can go a bit faster. How do we scale up, right? We want to be able to have contextual motion, have all those multimodal observation. We want to have the dynamics, but at the end, we want to have all of them. We want to be able to scale up with a different diversity of motion. So the way in our lab, we focus on, there's many different ways to do it, but the approach we focus on is leverage cheap wearable sensors. So in the past, we have built this IMU-based sensor motion capture systems that require 6 IMUs, and then it can reconstruct full body motion. How do we do that? Well, you do need to train a model offline so that sparse IMU sensors allow you to reconstruct a full body motion. So this is in the past. This year at CPPR, we expanded this work a little bit. So now we want to have a one single model that can handle, that can reconstruct motion based on different number of IMUs or arbitrary setting of IMUs. It doesn't matter where you put IMU on. We want to be able to have one single pre-trained model that can handle all of the different scenarios. So you can use 6 IMU, 4 IMUs, 3 IMUs, doesn't matter. At the end, it's really just like one single model that can predict the full kinematic reconstruction in real time. And we use diffusion model again. So same idea, diffusion model, think about all those IMU trajectories like an image. Each row here is a 1 IMU trajectory. And during training, we train 16 IMUs. In general, 16 IMUs can give you pretty good full body reconstruction, kinematic reconstruction. So training set, we have all of that. We use XSense or AMAS, virtual IMUs to create a data set. Now, during inference time, maybe you only have 3 IMUs, right? Like in this case, the person has IMU on the right hip, on the left elbows, left knees, and those are the signals that are provided. You think about the images where the portion, the images that are, the pixels are provided. And then the trained diffusion model will just fill out the rest of that. And now you have 17 or 16 IMUs to reconstruct your motion. And if you have a different combination, or you put you have 6 IMUs instead of 3, then you can do the same thing without retraining the model. Okay, so this is a work, collaborative work with Scott Delp at Stanford. And here my student is trying to use 6 IMUs. This is Tom, by the way, he's here today. We'll give a talk, his poster presentation later, SVPR. So now we just remove 2 IMUs. You only have 4 IMUs using exactly the same model. And we're still able to reconstruct motion in real time. Okay, so this is funny because I didn't know Richard's going to talk about this project. So I actually work on this project, Richard. He probably didn't even know that before. So this is a collaboration with Meta Reality Lab, HD 2D, to reconstruct the full body kinematic poses using just one single cameras and IMU and SLAM-enabled IMUs. Okay, so the one last thing I want to say, because I'm running out of time, is that there are definitely other ways to do it. For example, leverage to collect 3D human motion in the wild around the clock. For example, we can use ample 2D data that's already out there. The reason I want to put this slide on is that we're working on that, but we're not experts in computer vision. So very happy to collaborate. If anyone is interested in this domain using 2D or some kind of a combination of a 2D and with wearable data, we're very happy to collaborate with everyone. Okay, so that is how I see we can get a data set that would be useful for embodied intelligence. We need to have a contextual motion, we need to have a dynamics, and we need to have lots of them. And happy to take any questions.
Thanks, Karen, for the wonderful talk. We have time for a couple of questions. Yeah.
The question I wanted to ask is for Joel as well, but I think it's even more with your data. How do you know that those wearables that you are using during the initial collection do not affect the behavior of people?
How do I know sorry, let me repeat the question. How do I know this wearable devices that are used to collect data reflect the actual behaviors of people? What is the ground truth? Is that the question? Okay, so yes, I think that's a really good question, because even the ground truth people believe today, like lab setting, optical based motion capture system is not ground truth. I know that because when we're building app biomechanics, the ground truth, if we trust the markers that we see from those lab motion capture systems, we will not be able to find a model that actually physically matching the markers. So there is always different sources for ground truth, and the more different ways you can collect the data and then put them together into an optimization to get your ground truth, the closer you are to ground truth. So I guess my answer to you is that we never really have ground truth, but how close we could do the ground truth really depends on a lot of things. And oftentimes we find the best way to get that is you have a mode, so like force plates together with the motion captures. And then you optimize them of the very different modality of the data together. And that's how you get closer to ground truth. So going back to your original question, yes, IMU data is probably not going to be the ground truth. If you really want to know that, one thing I think Aria was doing, or certainly Neria is doing, is that they collect both the full body IMU data together with the others like headsets and tracking, and then have the different sources of ground truth and try to make them negotiate with each other.
People themselves behave differently if they wear something.
Oh, that is your question. I say, like, how does the devices change your behavior? Is that what you're asking? Yeah, so that is a very interesting question. I don't believe that those markers will change your behavior significantly, but I cannot really say for sure. So that's one reason that, when we collect different kind of activities, we try to design those sensors that's less intrusive. So for example, the diffusion poser has that design in mind. We want to be able to let the user choose where they want to put IMUs for the motion of interest, right? If you're doing soccer, maybe you don't want to obstruct your leg motion. If you're doing the other type of motion, that you have other choices. So that's kind of what we do.
Okay, so we are out of time now. We can keep the other questions for panel discussion. We will actually take a very short 5 to 10 minute break now, stretch your legs, and then This pioneering research spans several decades, and if you work on 3D humans, you probably already know him quite well. So with that said, please join me in welcoming Michael to the stage.
I shared audio. Can we test to make sure it's fine? Okay, good, good. I'm really excited about everything. It's a very exciting time, and the work I'm going to talk about here is a mix of things done at Max Planck and also the startup Meshcapade. And what I want to talk about today, I'm not able to control my screen. There we go. About foundation agents. So what's a foundation agent? Well, you probably all know what a foundation model. Wikipedia says it's a machine learning or deep learning model that is trained on broad data such that it can be applied across a wide range of use cases. So what's a foundation agent? Well, a foundation agent is a foundation model that has some form of agency. That is, it's embodied in some way and can interact with and affect the world. So what's a human foundation agent? This is a humans workshop. Well, that's an agent that can interact with real or virtual humans and worlds, and for which the embodiment, actions, and motor behavior are lifelike. So there's lots of embodied agents out there that play Atari games or do robotics and so on. But we're going to talk about ones that are embodied in a way that's like a human, behaves like a human, and interacts with humans. And why do I care about that? Well, it's pretty much all I care about is the humans. They're at the heart of everything. And I love studying them because our interactions with each other and the world are rich and complex and meaningful. And so what's a human foundation agent? Well, it's going to have at least these 4 parts. There'll be a 5th one later, but 4 parts, which really are in a sense, analogous to things that humans or other animals have. It's going to have perception, the ability to understand the 3D world and the motion of it and people in it. It's going to be able to reason about behaviors of people, what they're doing, why they're doing it. It's going to be able to generate motor behaviors and interact with the world to achieve its goals. And it's going to be embodied in some way. So I'm going to take us through these 4 pieces. And the first one being embodiment. We'll start there. We need some kind of representation for effectively our robot. But our robot, in this case, is going to be the simple body model, or SMPL. It captures basically everything we need to know about humans in 100 numbers, rough give or take. And effectively, it is a very compact representation of body shape, body pose, and our movement. So here, every single frame of this video, this is on the Meshcapade Me site. You can go play with it. It's just 100 numbers, right? And this effectively gives us a language of human motion. And it focuses here on behavior, not on appearance. We'll talk about appearance also, but this is really focusing on body shape and behavior. And I like to separate the representation of the human from the rendering of the human. I think those things are we often confuse those. Rendering and representation often get merged together, but I think it's really useful to separate them. Simple can be used, it's a traditional graphics model, it's a mesh model. You can retarget it to, this is Unreal Editor for Fortnite. You can use it to control game characters easily, but you can just as easily use it to control a video diffusion model, for example. This is work, Champ, and there's a lot of other work coming out now that uses Simple as a control signal effectively for generating realistic animations. Or you can do what the Hugs paper does here, which is use Simple as a foundation for Gaussian splatting. So this is work by Mohammed Kokobas and his collaborators at Apple. Mohammed is both a Meshcapade and a Meshcapade employee and still a grad student in perceiving systems. And he's giving a talk or poster on this tomorrow morning, poster number 32 in the first session. So check out Hugs. But I want to talk a little bit today about traditional graphics because I really like traditional graphics. I know everybody in this room probably is excited about neural graphics and all kinds of fun things, but traditional graphics actually works pretty well. So, you know, you can watch a movie with a synthetic Will Smith, and you can't tell the difference between the real Smith and the real Will Smith and the synthetic one. And so there's really like nothing wrong with traditional graphics. The only problem with traditional graphics is it's super expensive, right? It takes, you know, months of work and tons of artists to create this. So, but can we just use AI to like solve that problem, to automate the artists? And so you know, this is a standard scene with a metahuman in it. What's interesting here is the hair of this woman is created by a generative model. Okay, so what's that? This is a paper that will also appear tomorrow morning called Haar. For those of you who don't speak German, this is a cute title because Haar means hair in German, and I'll just run you through what Haar is about. So yeah, that's poster number 442 tomorrow morning. So the idea here is, well, let's not, you know, if you went and created Nerf hair, which we've done, or Gaussian splatting hair, which is also worked on, you know, that can look good, but you can't just immediately put it in a physics engine and have it work in a game, right? And that is pretty nice if you could do that. So what we do here with Haar is we take strand-based hair models and we encode them into a latent hair map. This colorful thing represents the scalp of a person, and the strands are encoded in some representation, color-coded here in this latent hair map. And then we train a conditional diffusion model that takes noisy latent hair maps and some text descriptions of the hair, and learns to take those text descriptions, take in input noise, and generate a latent hair sample, which we then upsample and then decode into a graphics-ready strand-based model of human hair. So how do we do that? Well, we take training data, synthetic data of hairstyles, we render them as images, we generate a bunch of questions about them. We use a VQA system to answer these questions automatically. We encode the answers, and we get an encoding of the text descriptions related to images of hair. Okay, and that then lets us say things like wavy hair or afro or faux hawk, which I don't even know what that is, and then the model will generate the latent hair map, which we decode into strand-based hair. And the neat thing about that is then you can immediately plug it into Unreal or Blender or whatever you like and do physics simulation on it. So you get all that hair dynamics. And then you could put it right into your game on your character and get nice looking hair, nice specular reflections, nice illumination, different styles, etc. Okay, so graphics isn't dead yet. I think using AI will revive it. Okay, so that's a little bit about embodiment, just a little tip of the iceberg. Perception is the meat of the story, and it really all began with this paper by Andrew Kanazawa. Jitendra is also a co-author on this paper, and it was HMR, and the basic idea is it has stayed the same since 2018. You take an image in, you have some backbone, you encode it into features, you train a fairly small network to regress something about the camera, typically a very simple model of the camera, the body shape, and the beta and the post parameters theta. And you typically do this by creating a 3D body model, simple body model, M here, taking the 3D joints, projecting them into the image with a simplified camera model, and then comparing them to 2D key points in the image. Alternatively, if you have pseudo ground truth data, you can penalize errors on the parameters directly, but that pseudo ground truth data is probably created from 2D key points. Well, that's a real problem, it turns out. And the problem is that camera model is wrong. And if that camera model is wrong, trying to make it your model match 2D key points gives you very nice projection into the image, but it gives you the wrong 3D. It gives you, there's a no free lunch thing here. If you've got the wrong camera model, you can either have good 3D and bad alignment to the image, or you can have good alignment to the image and bad 3D. You can't have both. And so we thought about this. Now, of course, the right thing to do is to estimate the camera. That's not actually that easy, and that's why people don't do it. But there's something else you can do, and that's token HMR, and it's poster 113 tomorrow morning. Everything's tomorrow morning. Busy day. So the way token HMR works is that there's two pieces to it. First, we define a new loss. So having 2D key points is pretty good. You want lots and lots and lots of data to train your methods. And 2D key points, you can get lots of it. And they tell you roughly what the body's doing. So that's good. But you just shouldn't trust them too much. You just don't want to over penalize. You don't want to get too close to them, right? It's okay to pay a penalty in your loss function for big errors, but you don't want to pay a big penalty for small errors. So that we introduce a new loss function. It's very simple that downweights small errors, but this introduces an ambiguity. It means you don't fit your data very carefully. And there's lots of solutions then in that space where right around the truth. And so you need some kind of a prior. If you take many of the classical priors, VAE priors, Gaussian mixture priors on pose, they all have some bias towards likely poses. So instead we train a VQ-VAE, which is relatively unbiased, and we tokenize the poses. And then we change the problem of regression into one of classification, basically predicting the tokens. And this actually works out pretty well. It turns the problem into from continuous pose estimation or regression into classifying these tokens. This is just a comparison between 4D humans or HMR 2.0 and token HMR. It could deal with really complex poses, which is great. You don't pay a big penalty in terms of accuracy for the tokenization. The accuracy you pay for tokenizing is way, way, way below the errors you get in existing methods. So check that out. But coming back to cameras and coordinate systems, it's really important if you want to interact with a 3D human. If you want to have a robot that's interacting with a person that's being perceived, an agent being perceived, then you have to be able to estimate the person in world coordinate system. So I'll tell you about this work, this paper, poster 184, Wednesday morning. I think I kept saying tomorrow morning. It's Wednesday morning. And this is work by So-Young Shin, who's in the audience, and it is the state-of-the-art method at the moment for 3D human pose estimation, as I'll show you. So here it is, speeded up a little bit. Notice that we have a moving camera, and on the right-hand side, you're seeing the person projected into a global coordinate system. The brown dots are showing you the trajectory, if you could see those. Basically, you shouldn't believe any results you see about human pose estimation if it's only in the camera coordinate system. You want to see it in a world coordinate system to see what's happening. So this is WHAM, and how does it work? Well, it's still going to use 2D key points. I didn't really like this idea, but it works, and I'll show you why. Well, I just said I don't like 2D key points. So we detect 2D key points in the images. We encode those with a motion encoder into a motion feature. That motion feature gets combined with image features. That's useful for getting richer information about the scene and the person. We have a motion decoder that is used to decode those into simple pose parameters. Okay, so that's pretty standard. The part that gets really interesting is we also run SLAM on the image sequences, or we use a gyro if we've got say an iPhone, and we get the camera's angular velocity. We combine that with the features, the motion encoded features from the key points to decode a trajectory of the camera. And then we also combine that with estimated contacts from the world. This is the contact probability you see here, and that refines the trajectory. And all of that together produces the person moving in world coordinates with a fairly accurate trajectory. So why do the 2D key points work out here? Well, it's a result of synthetic data. In Karen's talk before, you heard of a mass. A mass is a large data set, and what we do is we take lots of mass sequences and camera trajectories, synthetic camera trajectories around them, and project the motion of the 3D key points into the image, so we get 2D key point sequences for which we have the ground truth, right? So we can encode those 2D key point sequences and then decode both the pose of the body and also the global trajectory of the body. And then given there isn't a whole lot of, so you can generate as much of that as you like. There isn't very much data of real images with ground truth 3D pose. So what we do is we take image features and we combine them and we fine tune this whole thing so that that improves stuff a little bit. But let me just, I'm running out of time to see that. So here's a comparison between WHAM in blue, Slammer, which is an optimization-based method in green, and Trace, which is another regression-based method in pink. And you can see the ground truth trajectory there, and WHAM does a pretty good job of following. Now, interesting fact, unfortunate fact in the field, if you look at methods that do 3D human pose estimation from video, in general, they are less accurate than all the methods that do human pose estimation from single frames. Now, this is crazy, right? Because you should be able to take information from video and do just a lot better job. But if you look at the error here, this is the Procrustes aligned MPJPE for a dataset 3D-PW, it doesn't really matter. You see that the temporal numbers are basically bigger than the per frame numbers. Well, WHAM changes that around, and we get state-of-the-art. Low is good here, obviously, and get significant improvement in the results. You can do even better if you use synthetic Bedlam training data. And just to show you that the 3D trajectories are also significantly better, just looking at one measure here, the root translation error over the entire sequence, we get about 7 meters of error compared to previous methods like Slammer, which are about 14, so twice as much. And then the big win here is computational cost. Ignoring some of the pre-processing and things, we run at over 200 frames per second. This is a log scale on the left-hand side, comparing WHAM with PACE, which is a recent method from 3DV, and Slammer, an optimization-based method. Okay. So that's it from the perception piece. Now I want to talk about behavior, but I won't have any time for this. So unfortunately, I'm just going to tease you with 2 papers that we have at this conference and tell you a little bit about them. Image is a new data set. It's based on the BEAT data set, but we fit simple X to it with accurate fingers and accurate facial motions. So it's quite a detailed conversational data set. You have lots of people saying the same things, different people saying the same things and doing it with different emotions. And we train a model that takes speech in and can predict full body gestures. And then the second paper on emotional speech-driven body animation focuses on being able to really disentangle emotion from speech and gesture, and so allow you to control character and change their emotional state and so on. So those are also on Wednesday, poster 96 and poster 172. Okay. So I'm basically skipping over that. And I want to come to reasoning because I think it's the exciting thing. Oh, I think it's supposed to be 12. Was that? 10 more minutes. Okay, perfect. Look, the world is super exciting. We've seen amazing, in the last 2 years, amazing progress in generative models of text, images, video. These things are easy to get, right? It's easy to label lots of text. It's easy to generate lots of text labels of images. And if you can't label it, you basically can't model it. So, and large models, I mean, what did we learn from OpenAI? They've taught us scale really matters and quality of data really matters. And so for things like 3D objects and 4D human motion, the problem here is that we just don't have a lot of data. We don't have that level of scale. And so one thing you could think, we should think, well, okay, let's just label it with text. But everybody should right now think about your pose that you're in and trying to describe it precisely with language. Okay, it's not that easy to do. And in general, if you look at images like this, you know, coming up with text descriptions for these is kind of was impossible, basically. And there's a deep reason for that. We don't have language, precise language for all of our motions, I think, because we don't need it. If I want you to make this pose, I will make this pose, and then you can copy it. Why can you copy it? Because you actually have a generative model. You have a motor system that can actually reproduce that pose. And when your brain sees me doing that pose, your brain, your motor system gets involved in thinking about it, in understanding it. So having a body means that we don't really have words for text. So the traditional approach won't work. So what we think of is simple, again, is our label. You know, it encodes everything in these 100 numbers. And then the question is, if we can label lots of data with this representation, can large language models actually understand it? Can they reason about us and our behavior from simple parameters? So that is the theme of this paper, Chat Pose, formerly known as Pose GPT. Name had to change because the reviewers made us do it. So it's a little confusing, but it's okay. There was another paper called Pose GPT. And so now it's called Chat Pose. And it will also be Wednesday morning in poster 186. So, and unfortunately, the two first authors didn't get visas to come in time, and therefore you'll have me at the poster, so come and say hi. So just briefly, I will tell you what Chat Pose is about. The idea here is you got an image like this. You probably can barely see what's going on. There's a guy in a green shirt sitting in a chair. So you can chat with Chat Pose. You upload this picture and say, is there a person with a green shirt? If so, please describe the person. And, you know, that's a standard thing that chat systems will do now. Yes, there's a person with a green shirt in the image. This person is sitting on a chair. And then you can ask, please give me the simple pose of this person. And it replies, the simple pose of this person is pose. It returns a pose token. Whenever we see that pose token, we take the embedding for that pose token and we convert it into a simple pose, a 3D mesh like this. And I'll tell you how we do that. But you can also say other things because Chat Pose actually understands a lot about people and what they do. So what might the body pose be when he finishes getting his hair cut? You can ask that. And Chat Pose will say, well, it's difficult to predict, as they always tell you that. But maybe he's going to be more relaxed and have a more relaxed pose, such as token pose. And so you get kind of a more relaxed, less upright pose, right? So how do we deal with this? So we take a pre-trained large language model, LLAVA here, and we normally you can, the normal deal is you could take in text and images and you get text back out, right? And what we want to do is take in images or text and get out 3D simple bodies. So we train this thing with detailed descriptions. This comes from PostScript. We have detailed descriptions with body poses. But remember, I told you that's not very good in general. So we also have images cropped images of people along with body pose. We use a couple different training sets. The detailed descriptions, we can actually at inference time replace them with much less detailed descriptions. For example, a man is proposing marriage. And because the network has lots of information about the 3D world and what people do, it can reason about this. We can also give it a full image and it can reason about, like, the fourth person from the left and what are they doing, right? So our first thinking about how this would work is, well, geez, we've got to have to tokenize a pose in the way we did with token HMR, and so that LLMs can understand it. But that turned out not to be necessary. And we can train LLMs to directly or large vision language models to directly reason about simple pose parameters by using a projection layer that takes that pose encoding and turns it into simple parameters. So, I've lost my audio. I don't know why. I will shout. I don't know. Okay. You can't hear anything, right? It's okay? I can't hear me. Something changed. Okay, so the model, oh, there, now I can hear me again. The model consists of a multimodal LLM, and it includes a vision encoder and a vision projection layer. And we train it with 3 different types of data. We train it with standard multimodal instruction following data, so it doesn't forget about the world and everything it knows about, like funny dogs on skateboards or whatever. And when an image is presented, we actually train it to output the simple pose parameters. We take the code encoding and we penalize the pose error. And when we're given text input and we have ground truth 3D poses, we have it predict the 3D pose. I think I'm almost out of time. It is not state of the art in terms of taking images in and producing 3D poses. It works, chat pose on the right, but it doesn't beat a state of the art method like HMR 2.0. But it does some really interesting things. So normally when you're training a method to predict 3D human pose from images, you do lots of augmentations, lots of, you crop the images and you do all kinds of stuff. We use no augmentation at all. And we take things like these highly cropped images where it's very hard to predict see what's going on. And the model actually does a reasonably good job of estimating pose. It knows enough about humans and what they do. So you can input text, and okay, I'll skip to something like you can input something like this, which is quite ambiguous. It's not describing joint angles or anything, what's in contact. A person is proposing marriage, for example, and it can generate a reasonable pose. Or you can have a conversation with it about what kind of exercises you want. You say, I would like to, it tells you to do some yoga pose, and you say, I'd like a more challenging pose, and it knows what challenging means and gives you a handstand, for example. But I think I'm running out of time. So the next piece of this, so I've described 4 things. The next piece is really interaction, and that means having everything running in real time so that we can have these foundation agents interact with us and interact in virtual worlds as well. So I want to leave you with a few takeaway messages. Simple provides an embodiment for the human foundation agent. You should separate you're thinking about the representation of the body from how you're going to render it. If you don't, then you're going to get hung up on all kinds of problems. Traditional computer graphics is not that bad. It's pretty good. And you can use generative AI to make it better. Synthetic data, which we used in WAM, is key to accuracy. It's key to accuracy in many, many other situations as well. It's important to estimate human bodies in global coordinates. And human understanding has to be fast. That's critical. And LLMs can reason directly about 3D human pose in terms of simple parameters. And they can actually then bring their world knowledge to bear on reasoning about what it is we do. So I just leave you with a few more things. We've got a bunch of other posters in that morning session on Wednesday. Hold, Wander, so Hold is reconstructing 3D hand interactions, 3D object hand interactions. Wander generates people moving realistically to achieve goals. Sculpt is a generative model of shape and appearance. And HIT stands for human implicit tissue. It looks inside the body. Given the outside of the body, can you predict not just the bones, which we've done in the past, but also where all the fat is and where all the muscle is. And then Wednesday afternoon, horses. In case you're tired of humans, we've got some work on horses. And then Thursday, generative proxemics, which is a generative prior for multi-person interaction. And one last plug for ECCV workshop. If you're already planning ahead, we've got a workshop on foundation models for 3D humans. So come to Milan and enjoy that. So that's it. Thanks.
Thanks, Michael. Lots of exciting stuff out there. So we have time for questions.
Michael, thanks for the talk. I've been doing some study on the non-action generation, and I recently have this issue about identity gap. It's like the motion captured on me, when it's applied to another identity, it looks a little bit weird. And the question is for foundation model like this, how does the generated post actually apply to another subject?
Yeah, it's a great question. And so the question for people who didn't hear it is really one about retargeting. How do you take the motion of one person, retarget to another person who might have a different body shape, limb length, and so on? It's one of the oldest problems in computer graphics, this retargeting problem, and there are really pretty decent automated solutions, but they're not perfect. So for example, one thing that none of the solutions deal with right now is if your body mass is different, you might move differently, right? So what does it mean to retarget a very light person walking on a balance beam to somebody with a much heavier body? Do I want to reproduce that person exactly, or do I want to somehow take the essence of what it is they did and then change it to a new physical form? It's actually a little bit of an ambiguous problem statement. But it's one that we are looking at this problem of retargeting with physical constraints so that the physics of the retargeted body are correct and still capture the essence of the original. That's a good question. It's a hard problem.
Maybe one more. Yes.
Do you think that height-based motion capture would give a picture of standard of based?
Yeah. Yeah, interesting question. We've done a lot of IMU-based motion capture, like the 3D-PW data set is based on IMUs. For that, we combined it with a single vision sensor, and that combination was really useful because they have different error profiles, if you will, right? And so you've got, in a classical probabilistic sense, if I've got an error distribution from one source and an independent error distribution from another source, I can combine those and I get a better result, which is what we did in 3D-PW. I don't know. It would be great. I would love a fully markerless thing I could wear around all day with no drift and not be cumbersome. It hasn't existed yet. And look, to get scale, even if everybody in this room put on an IMU suit for the whole conference, it's a drop in the bucket because you're probably not jumping off a high dive and doing all kinds of other stuff, right? When we think about internet scale that OpenAI uses, it's a whole different ballgame, and I really want to capture everything that's ever been done.
Okay, great. We have opportunity for more questions in the panel discussion, so we'll move on now. With our next speaker, it is my great honor to introduce our speaker, Professor Jitendra Malin. Jitendra is Professor of Electrical Engineering and Computer Sciences at the University of California, Berkeley. His foundational work has deeply influenced our understanding of many subfields in computer vision, machine learning, and robotics, including all aspects of 3D human understanding. Jitendra awards
It's free.
Hi, everybody. People who come in late, I mean, there are Some questions. So, discussions and questions from the audience as well. So, the first question I have is, what is maybe the problem or a concept or an idea that has been most exciting about you that you're most excited about these days? What is the thing that really has excited you and has motivated you to work in this direction? You might have worked on this already, or not, or you want to work into the near future, but something that has been exciting for you. I can pass the mic. This is live. I think this is if you do any order. Okay. Start from there. I think I start from the lady, but
I'll just start. There's so many, but I'll just take one. So I am very interested in studying human peak performance from many different angles. Definitely from computer graphics, character animation, but also from biomechanics perspective. What makes someone just faster, stronger, and perform better? What kind of performance? Graphic performance, it could be musical instrument performance, and want to understand from that perspective, because a lot of the science and engineers were improved because of we are very obsessed with studying elements, signals, right? In the past century. That gives a lot of the advancement in science. But what about the other end, the other extreme? That's capture their emotion, reconstruct the emotion, and really build a digital twin study like that.
I think the thing that I'm excited about most is finally seeing some of this physics simulation based post estimation actually working. Because in the early days, like we spent like 6 months just trying to design the humanoid, couldn't get it to like stand. And then we had early like physics models where like we got just the humanoid to walk, and we're like, oh, it's walking, it's not falling down. But now we see like all this like dancing, picking up objects, and just seeing those advanced over the last couple of years. That's really exciting to me.
All right. So inspired by the text-based internet scale next token prediction, that I'm pretty sure 20 years ago, most experts in the field would have said would not have yielded the types of intelligent seeming behavior. And also that at big enough scale, it seems to also capture something about 3D, but it certainly misses a lot. And then next is the fact that you're kind of running out of tokens on the internet, that kind of data. There's only so many Wikipedia pages, only so many top textbook blogs. So then with the 3D humans and egocentric data in particular, it's really the new data source. So in a sense, the new PhDs are starting to look at this problem, but under the guise of possibly next token prediction, but 3D. It's very exciting. I mean, I'll leave it to you as to whether or not you think that reality is predictable and to what extent it is. But I'm inspired by the idea of the combination of generative AI, making videos, but conditioned on your life, such that you could see the future video of yourself achieving whatever it is you so desired, in a kind of like directed video cut of like what might happen next. And that might be one of the most ultimate interfaces to computing we could have. Seems like these things are coming together.
So I'm very excited about what we as a field have achieved. I think, as I said in my talk, 3D humans are something which probably the first paper in computer vision or graphics is, I think, David Hogg, 1983, a program to watch a moving person and something. I think that's probably the earliest that I know something earliest. So how many years is that? That's like 45 years or something like that. And people will keep working on making it better and so forth, but to my mind, we are really ready for using it.
And in my mind, the thing which I'm most excited about is to use a combination of imitation learning and reinforcement learning to solve robotics. I think that robotics has sort of missed out on the big revolutions in big data. Like the AlexNet moment happened in computer vision. For NLP, probably the big moment was Transformers and BERT. And but then they went ahead of vision, I would argue. And but the robotics people sort of don't quite have that. But I think we can give it to them. Okay.
That's special. Well, I'm never giving it back. So what, since the beginning of time, we've been looking at humans in little bounding boxes, away from the world. We've been modeling just the human, and with the exception of recent work, like hand object stuff, we pretty much ignore the whole rest of the environment, the interaction between people, and that's not the real world. And we do that because it's very hard to model all that stuff. And so what excites me is the fact that we now have these large vision language models that, or even world models that have been trained on video, that actually understand a lot about 3D scenes, interaction, and it excites me to exploit that kind of understanding to really attack this human understanding problem.
Amazing. And follow-up question to that, and we don't have to go in order, like if someone wants to chime in, feel free to answer. So the question I have is if there are some types of problems that you think that deserve more of our attention, and if there are problems that you consider as solved or close to be solved in this area. So question more about the more open and closed problems in this space. I think with what you answered already, we have the layout of open problems at least, but if you have other thoughts about both open and closed problems in this space. And this is directed towards question. I imagine a question from the first year PhD student, like what problem do you advise me to work on, and what problem a student does this point.
I don't think any of them are really solved to the level that's, it depends on your goal, right? But if you define a task, some of these things might be solved, but the tasks I care about, they're not solved. So, for example, I care a lot about humans interacting with each other. Their facial expressions, the gestures, precise timing, the contact with each other. We don't have good methods for these yet. I mean, we have all kinds of impressive results we saw a lot today. They don't really capture the nuance of real human behavior. So I think that there's
yeah, a lot to be done. There's a lot where we're just at the beginning because the data sets are only starting to exist, be eccentric or not. But here's a thought. I think, well, if I was to answer what would I do again if I had my time as a PhD student, with today's data, today's compute, I think it's one of the classic questions of representation that I'd open back up again, because we've got a lot of techniques where if you do choose a specific representation to solve a particular task, kind of the tools are there. If you can build a data set, you can kind of nail the problem. So now the question is, well, what if I don't know what the problem is I'm trying to solve? What we humans seem to be able to do on the fly is construct representations that are just right, just efficient enough to get the job done. And there might be something very explicitly, something valuable about explicit representation, for example, the difference between a human and the thing they interact with. But I bet that's wrong. I bet that's just a moment in time that we're in. So, if you have a look at the segmentation space, where Segment Anything came along and basically went, this problem of segmenting a single image.
Evidently they can still hear.
Okay, you can still hear me. A single image segmentation used to be things that people would spend their PhDs on. Oh, this is grass, this is a cow. Chandra, I'm sure you have a lot of students on this. And we knew it was wrong. What is grass out of context of the query? But that's what we knew how to do. Then segmentation only came along and said, oh, okay, here's a prompt conditions, segmentation. Everyone was like, thank God for that segmentation problem is now a better, well-defined thing. But it's like that for all representations and all tasks. And it's almost like we haven't really understood how to ask the more general problem. It might be quite far off for high performance work. My team still use SLAM systems and we still calibrate cameras and all this sort of thing. But at some point, we will have more powerful representations where for any given task and query, the right kind of representation is brought to bear fluidly. And I think that's a big challenge, especially when we're just at the beginning of performing humans. Didn't work anything.
Great. And another question I have is, and this also relates to how people react to some of the developments that we see, not just in our area, like this more narrow area, but more generally in the field of computer vision and AI. The question is if there has been something that has really surprised you the last few years, something that the direction that really took off, or something that started working much faster than what you expected, and how you reacted to that, like how you planned forward after some development. Because this is what many people dilemma or the unpredictability of even the near future that some people see. How did you react to
in my mind, in the last 15 years in AI, there have been only two big surprises. One was AlexNet, and the other was scaling behavior from GPT-2 to GPT-3. Everything else is a corollary.
I mean, I agree, but I think the question is, how do you react?
How did you react so that to effectively
With humility.
I think with humility is important, but there's humility.
I disagree.
If you could be. I think if you're still up here, you probably got excited as well, right? Initially, when AlexNet came out, we were trying to apply these techniques to 3D human pose estimation, and they weren't working. I actually believed for a while that neural networks were not good at dealing with continuous rotation parameters. I just thought, yeah, we can't make it work, we can't make it work. But of course, now we use it all the time. And I think you have to, as a scientist, when dramatic changes come along, you have to understand them, embrace them, and try to figure out how to take advantage of them. Seems obvious, but
I'm going to add one more thing. Things that surprised me the most in the last decade or so. In general, the data-driven approach versus the physics. I built my entire career based on physics simulation. I wrote my own physics engine. So I would never guess that data-driven approach would reach the, to the point that I can't really strongly advocate for physics anymore. But I think there's also a lot of opportunities it opens up. So for example, even though we're doing a lot of physics simulation, it's not really physics engine designed for simulating human motion. If you look at all those contact forces, joint torques that you get from your physics engine through reinforcement learning, they're not really human. They're just one solution that fits human motion. So I think a data-driven approach will actually be a very good complement to physics engine if you really want to study human motion, because it's really hard to build a human digital twins in this physically correct sense. And we really need data to help us either system ID, the human model, or just in general, there's a lot of physics equations we not understand very well. Data.
So maybe this is a very kind of meta level observation, but what surprised me in the last couple of years is how much money can advance research. So putting in a lot of, of course, there's brain power, there's compute, right? The money brings all of that. And then you can have these breakthrough moments. That was pretty surprising. I guess in the past though, you think about an Apollo mission, this is things that people have done before. So
okay, so what has been my reaction to this is join places that are like well-funded, huge projects, lots of resources, but at the same time, within academia, find those problems that are like, they're so cutting edge that it's not time to do like this massive investment and kind of innovate there. So it's been kind of like this two-pronged approach.
Maybe I'll respond to this. So in my view, people have to figure out what their comparative advantage is. And the comparative advantage in academia is different from industry. Industry also depends on your company and are you in a lab, are you in a product unit, et cetera, et cetera. So always think carefully about that. AlexNet is an example of the success of pure academic research. I mean, it's 3 people with 1 GPU, I mean, in a university lab. Okay. On the other hand, ChatGPT is an example of industrial research, right? Tons of people, you know, $1 billion of compute, etc. Is one superior to the other? No, they're different from the other, and there's room for everything. And you have to figure out what makes sense given your resources, skills, talent. So take the combination of your ability and some sense of what will have the biggest impact, and try to figure out this equation. Okay, where is your ability to influence high, and take the product of that with a likely impact, importance, which is going to give you the impact. So think about that, and I think that we all have to think about it in our own settings. There's no one size fits all answer. So there are probably right now approaches which are being tried in academia with like a lab with 2 students and 1 professor, which may turn out to be very big deals 5 years from now or 3 years from now. We have to be open to that. We should not think that all the wisdom right now is in the hands of 5 big companies, even though I work for one of those. Okay.
Sir Otis. And okay, that's the topic segment. Yes, but I think research is often requires a lot of money. I was wondering, is there a project, if you had internet money, is there a project like that you would really invest your money towards, like a research project? And this is from the I have seen like different directions how people have done this in the panel. Someone would get the better sensor, the more accurate sensor. Someone would really try to collect a lot of data or try to collect the data as much as possible. Is there a direction that you think that would be just solved with money? Where would you invest your money in a research project?
Yeah, as Jitendra was saying, at least 3 of us here work for the same company. There's lots of money in the the research space for wearable devices. The thing I'd caution about though is kind of like, what's the right time to worry about the money and the equipment problem? So even when AlexNet was going on, certain conditions had to have happened. So NVIDIA had to have invested in GPU programming and supported something like CUDA, at a big enough scale so it wasn't just falling over, so the PhD students didn't have to like write their own GPU compilers and so on to such an extent. ImageNet data had to have existed, which required a big effort from Faith Bailey and Co, I think. And even that itself is standing on top of what the apparatus was that they collected that image data with, which itself is a function of social media and the ability to have smartphones that are worth putting cameras in, because the market was there for people to post their images with captions in. So I caution against this idea that there's a difference really between industry, engineering, and research. I think it's extremely rare. In fact, I've only been in it for 20-something years, and I can't tell the difference. Now, it might be different in other areas, perhaps in deep physics, theoretical physics, but we're not in theoretical physics, we're in a deeply applied area. And your research and everything that we just talked about, is like 2 big things, are completely dependent on hardware that was developed for other consumer reasons. So where does that leave us in terms of like, what would you do? Well, actually, sometimes you've got to be part of a product cycle to build the new equipment that goes to enough scale, so then you get a new generation of data or a new type of compute. So at some point in the future, I expect us to have glasses that really do have the cameras on, that are useful for collecting new generations of data set way bigger than, say, Project Carrier, which will never get more than, there's 5,000 devices in the world, and hand them out around as much as the developers. As we said earlier, that's the drop in the ocean relative to internet scale. So think about that. Sometimes it takes a product to actually launch new research, as we call it, computer science anyway. But I am excited if perhaps around the corner somewhere is some, new PhDs who are thinking about completely different from the current sort of like generations of data-driven, massive scale data. If it's always going to be more of that, I'd say probably we've got to build a new generation of product that gets us the right kind of data. Or make an incentivization as to where this data is going to come from, because that's what's driven the current revolution.
Yeah, maybe I'd add one thing, which is that I think it's something that all three of them refer to. I think tactile and haptic is very important, but it's really under-resourced compared to vision. I mean, I think we are all sort of visual chauvinists, maybe not Karen, but where most of us are because of computer vision. But this is not all there is. I mean, I think touch is very important, haptic is very important, and we just want to have really well-working gloves which are in the hands of millions or billions of people. I think knowing about forces would be very good. So and these are things where actually I think there is innovation possible at all scales, from very pure to very applied. I just wanted to put in a plug for that because I feel that's quite under-resourced.
Yeah, so I think, the way that you set up the question was if you had like kind of infinite resources, like what would you work on? And what I was thinking was, at least in my case, it's not so much the resources, it's time. I wish I had more time. If I had more time, I could do, more investigations into more areas, find more connections between different threads. And I feel like that's like what's holding me back. Yeah.
I think you can buy time, you have money. And that's what I want money for. And this is not a lot of money. $1 million for each PhD. And that's, I feel like, where money can actually go a very long way, not just today, but many, many decades. We really have, there's just so many postdoc PhDs out there I want to work with. And I also want to never worry about equipment in terms of robotics. Like if I want a humanoid, this is also not a lot of money, right? Like, and then every single lab out there, they can do this somehow, funded by big companies. And that will be
We should throw it open to.
Yeah, is there any other questions from the audience here?
I have a question. Does anyone have any ideas how you can kind of systematically increase the kind of accuracy and fidelity of lots of the computer vision methods? For example, I'm thinking to Michael's slide of the computer graphics with Will Smith there. I think for graphics people, the bar for is it working or is it solved, it's like, does that look like Will Smith or not? And currently right now with a lot of computer vision, we've got errors of centimeters, and we've got flickering on the characters, and we haven't got fingers or toes and stuff. So it's a very long way from like, is that so convincingly Will Smith that no one can tell the difference?
Yes, you're from computer graphics.
Yes.
This is a simplified question. The quality is just not good enough. I mean, they're amazing, thinking of where you came from. But from computer graphics, we were okay, that it's processed and it goes somewhere. But what is planned to push it all the way to 100% from maybe 90%? That's it, actually. I like to know too. Is it data the solution, or is something else?
Yeah, so I have a position on this, which is that this is there is no such thing as 100% accuracy. Okay, I mean, physicists have the right notion for this, which is you're doing an experiment. Your experiment is to prove some hypothesis or verify or disprove some model. So subject to the needs of that, a certain accuracy in your equipment is good enough. So I think what we are doing here in our business is that, like when you build a program which looks at a human and estimates the 3D pose, you are building an instrument. It's like a microscope or a telescope. Now, how good does your microscope or telescope need to be? Well, it depends on the application. So I personally feel that, so there will be a trade-off between fidelity, which is how accurate you are, versus scope, in the sense that how widely is your technique applicable? Can you throw any video at it, or is it a video collected in a lab against a green screen, and so on? And there is no right answer there. I mean, I personally am biased, and I've often given talks before or after Michael's, and he's always on the side of high fidelity and doing things in labs. And I'm a believer in, I've never bought a Vicon equipment or any motion capture ever, and never will I do it. Okay, I only want to do it from pixels, and I'm willing to accept lower accuracy for the sake of broad coverage. But this is not a debate which has only one answer. It depends on what application you have.
It does depend on the application. I bought my first Vicon system many years ago with the idea that I would get rid of it by solving this computer vision problem. But I still have Vicon systems because it's sometimes useful to have that package. What we do in computer vision is we set up, we make up problems. We don't really solve real problems. We make up a problem. We say, oh, we make a data set and you're supposed to do well on this. And then everybody does that and the numbers get better and better. But if you take any of these methods that we talk about here and you run them on, I take a random movie and I run them on it. They're going to fail on many, many, many frames. But not even a little bit fail, but fail in a major. So we're a long way from really having both robust and really accurate solutions, I think. And the challenge for the community is to now pick the next challenge. So say we run this out, and it looks good enough from a computer vision point of view, everyone's so happy. Now we need a new benchmark, new challenge, new data set, something that drives the community to the Will Smith level or the physical forces level or whatever it is. That's how we make progress.
Question. I work mostly in 3D face generation from animation. And one of the biggest issues we have there is you can get really high accuracies in vertex reconstruction or displacement vertices to animate face. But capturing those really small nuances in facial animation, the subtleties in the eye motion or the lips or the cheeks, even your brow raising is very, very hard to capture. And so you can get really good vector performance, but those nuances, when you think about something, you get the uncanny valley. So where you guys kind of see the roles or the ability to build sort of AI critics or critics in the loop that can handle or evaluate those nuances and get more towards the abstract notion of what the motion you're looking at and how that relates to how we perceive motion, how we sort of interact. And I guess this is kind of getting to where kind of chat pose is going and stuff like that. So I'm just kind of curious on your thoughts on that.
Yeah, I would love to have some sort of, I think you're hinting at some sort of almost interactive learning system. I think this would be super great. That's not what we have in our hands right now. But we have things, you get a massive amount of data and you train it for a long time and then you generate something. If I'm interacting with you and I'm behaving in a weird way, I'm getting signals from you that I'm behaving in a weird way and modifying my behaviors. We don't have that kind of real time. It'll never be good. And it's not, we think a lot about appearance, but timing is everything in human interaction. The timing's off. Everything just feels wrong. And it doesn't have to be off, but you're not coming back. But the previous question, small inaccuracies in the timing and communication, setting all of those things.
Yeah, I think also I point out that there's very few methods available to actually capture reality outside of very specific lab settings. So if you've seen Yasser Sheikh's labs work on codec avatars, you'll see the sort of like 200 gigabytes a second capture rates that are necessary. And they went to great lengths under the simple principle that was, if you can't measure it, you can't improve it with respect to fidelity of human avatars. And this is all in practice very hard to then translate to any other than like very small scale labs, because it's got to in the end come onto a consumer device to be valuable. And we're back to the who's going to spend billions of dollars on that same equipment for their own lab if the hook is uncertain. So it's just also that we look at how we might really capture what humans are looking at. Which I think is like one of the other answers to the questions earlier is what surprised me. What surprised me is how few computer vision people seem to care about how humans look and see with their attended vision systems. And it's because we're incredibly biased, not just image chauvinist, we're photograph chauvinists. We think of it as computer vision as coming from sort of like photographs first, and then maybe video if you're a bit, risky. And then maybe robotics if you're really fringe, and then this new egocentric thing. Well, I'm not sure about that. We've got a smaller room around the corner, we've crammed in there, right? But all of that is still using non-foveated sensing. And even though ARIA's been around now for sort of 3 years, very few people have used the eye tracking to actually look and see what are people looking at, what are they attending to, when, for example, watching videos of things that may be in the uncanny valley, and doing so at a big scale, let alone trying to develop foveated imaging systems. And what I mean by that is, you could drive something like Project ARIA by just only capturing where the person is looking at very high resolution. Now, beyond that, there's kind of problems with it, even capturing the physical limits that humans can capture. Our eyeballs are this big for a reason, get smaller, and then sort of like the diffraction limit starts to come into play where you can't even capture the details you can see. And that is a real challenge, both for like actually display, and it's better to know that because Apple did a really good job of retina resolution displays and telling people about it. But imaging systems, there are very few people who actually have imaging systems in their labs that can capture what a human can actually see in the conditions that we can see it. So I think that's the challenge of data sets, because then if you can't measure it, you can't improve it, you can't capture it.
I think we are right on line. Then I have one last question. There were many interesting nuggets that were heard during the panel discussion. What I would like to ask as a closing question is if you have any words of wisdom, particularly for more junior people in this space, for someone starting their PhD. And again, there were some very nice nuggets heard already. But if you would like to say something to someone starting their PhD or and finishing a PhD soon and thinking of future opportunities, something that you'd like to say to them.
Yeah, you should go first.
I like to reinvent wheels. So don't be afraid to reinvent wheels. I feel like that is a kind of attitude that has negative connotation, but if you really think about that, when you think about a problem to work, I don't know, early 20s, you probably never came a solution to that. And before you just jump into looking for a solution that other people have solved, try to work on that yourself. You treat it like a puzzle, see how far you could go. It might be a waste of time, but probably a lot of, this exercise still lead to paper publication, but only 20 years old, you're so young. You have time, a long time in your life to explore just for the fun of a puzzle solving.
Yeah, I would say one thing that you might not realize as a junior researcher is when you're doing independent research, you can move really fast. I guess you see the flip side of that when you're an organization that has a lot of people working on like a big problem. I would say take advantage of that. And the other one is just like enjoy your research. Like just get into it, dive into it, have fun. Like this is like a really special moment in your life when you're just like, by yourself doing research, like just enjoy it.
Yeah, I think it's funny, we all sound what's the word, like old bogies who have had the grass is not always greener. That's what I'd say. So, you know, if you're in a lab and you don't have a lot of compute, you don't have a lot of data, use that to your advantage. You know, I wish for the days, it sounds like ridiculous, but I wish for the days when there wasn't such a need for such vast amounts of compute and data resources to do novel work in conferences like this. And the reason being, because actually the research cycles slow down tremendously, even when you are, you know, quite independent PhD student. There's just so much more out there. There's the intersections between neuroscience and computer vision, between robotics and neuroscience. In fact, you know, these are really the spaces that are going places. I would suggest if you see companies investing billions of dollars, that's the time to get out of that research game and get into something that perhaps looks very much more risky. Once upon a time, working on AI was a surefire way if your department head sort of have a conversation with you about your career and that you should be doing something serious. Now I fear we're on the wrong side of that, where department heads fear talking to their PhD students about what real research looks like. You know, so I would say the grass isn't always greener, and you're probably lucky if you're in a lab that's not been painted with requirements on massive data and compute to do anything in the department. Look to the areas that are still fringe and perhaps, you know, getting more fringe because of the current hype that's going on in Gen AI. Neuroscience is, I think, a very fertile space right now.
I actually agree with much of the wisdom that has been articulated here. I will state the two things that I tell all my students. Number one is take risks, and it's okay if your project fails. At least in your PhD, you can do this with impunity, and you should. If every project of yours is succeeding, your bar is too low. Your success rate should be like 50% when you're doing your PhD. Okay, write few papers, but surprising papers. And surprising papers come when you work on things where there's a reasonable probability of failure. So you may fail. If you succeed, it'll be worth it. So that's point one. You don't need to. Why do we write so many damn papers? Write fewer papers. Take risks. Okay, you can do it as a PhD student. Okay, when I got my job at Berkeley, I published one paper in a refereed conference period. Okay. Second point is be interdisciplinary. I think this has been alluded to by Richard. Really, I mean, I have got my greatest enjoyment and inspiration from reading the literature in psychology and neuroscience and various other fields of computer science and so on. And that way you'll never be out of business, because if you have a certain breadth, you will keep moving and you will move to where things are interesting. And be open to going to murky waters. If you only swim in clear waters, you're going to see the same thing that 99 other people are seeing, and you will be but one of 799 papers at this conference. Okay, try to be not that. And you can do it just by being willing to take risks. You do not need to write 10 papers in the course of your PhD. Just write a few good ones after having failed at some.
Yeah, all good advice. You know, I think about successful scientists who have long careers, and they all sort of balance two very different seeming things: stubbornness and flexibility. You have to have some level of stubbornness to stick to your ideas and keep driving them, even when you have failure after failure. But at some point, you also have to be open to the idea that maybe it's the wrong path. You have to know when to pivot. Or you have to say, well, my idea is right, but there's new tools that have come along. I'm going to just throw away everything I've done and use some new tools. That balance is something that's very hard to strike. And if you strike it, then you can have a very successful career.
Okay, so we're all very lucky to have all the panelists here. Let's thank them again. And I think there is a presentation after this in the arts, city, so.
Yeah.